Yeah, brother, it's that time again.
Yo, what up, Gally? So this is introducing a new application for the celestial theodolite here. I'll let Brian take it away and explain what he's got going on.
Hello, this is Llamazing, and I'm going to present a new application for the celestial theodolite today. But first, let's recap what it is for those who don't know. The celestial theodolite uses observations of stars setting behind mountain peaks. By noting the exact second where the star was no longer visible, you can then consult an astronomical almanac to determine the uncorrected angle to the star at the time, as in not influenced by refractive and other optical effects. By forming a right triangle at the base of the observed mountain, with the other 2 points at the observer and the mountain peak, the geometric angle to the mountain can be easily calculated using basic trigonometry, where the angle is the arctangent of the height of the peak minus the height of the observer, for this vertical distance divided by the ground distance, which is also going to be equal to the angle to the star from the almanac. It is interesting that the physical angle to the peak of the mountain comes out the same as the almanac angle to the star, despite there being no allowance for Earth curvature in the calculations. Most of the observations are done at long enough distances away that the amount of ground curvature would be significant. When the calculations are done using globe math, and that accounts for the curvature, the numbers are off by the amount of ground curvature present. Refraction, the bending of light due to the changing density of the atmosphere, has to be invoked to compensate for that difference, bringing it back to where it would be without the curvature. The following celestial theodolite measurements have been made to date, sorted by observation distance. The farthest one done so far has been to North Peak in Colorado, with a distance of 130,000 meters. But instead of discussing stars getting occluded behind mountain peaks today, let's try something new and completely shatter the current longest distance observation, which is going to be 7.7 million meters, which is 60 times the furthest record to date. And here's what we're discussing: solar eclipses. A total solar eclipse occurred on April 8th, 2024 in the United States, with totality lasting from 4:30 p.m. to 8 p.m. UTC time, and that was 4.5 minutes at any one given location. Noteworthy cities along the path are Austin, Texas, Dallas, Texas, Little Rock, Arkansas, Indianapolis, Indiana, Toledo, Ohio, and Rochester, New York. The path was going from the southwest to the northeast. And then, of course, the sun and moon are traveling from the east to the west. And the reason that the eclipse path travels from west to east is because the sun outpaces the moon, swinging the shadow around as it passes. The reason the path of the eclipse travels north is because the sun is getting farther away from the moon, making the angle of the shadow down to the ground more shallow and thus farther reaching. So now we've got to understand the eclipse. Where to begin? First, I want to understand why the path of the eclipse shadow would travel to the north. So the first thing to do is study the movement of the sun and moon in Stellarium, which is a planetarium app showing the position of the stars for a given location and time. Starting at the farthest point for the eclipse shadow, I drew a great circle route to the moon. Then at intervals of 1 nautical mile, which is 1/60th of a degree of longitude, I used Python to calculate the latitude and longitude coordinates for each of those interval points. I also recorded the observer's altitude angle to the sun and moon, which excludes refractive effects. And then I plotted the angle versus ground distance for both the sun and the moon. So starting here with the sun, the first step is to create a linear trend line of the plotted data, which you can see is this dashed blue line. And the R value is high, indicating it's a good match, or close to 1 rather. The slope of the trend line gives rise over run, so the slope value of -9 e to the -6 has units of degrees per meter. Vertical is degrees, and the horizontal is millions of meters. When we take the inverse, 111,000 meters per degree, and then divide by 1852, which gives us 60.038 nautical miles per degree. This is close to the expected 60 nautical miles per degree, where the sun drops by 1 degree for every 1 degree of distance traveled. Going back to this 111,000 meters per degree number, if we multiply by 360 degrees to get the circumference, and then divide by 2 pi, we get the radius value of 6.3 million meters. This is close to the 6,371 radius for the Earth value, which is what we'd expect. But now when we go to the moon, something interesting happens. If we generate the trend line right before, this gives us 9.13 e to the -6 degrees per meter. Invert to get 109,000, and then we divide by 1852, we get -59.1327 nautical miles per degree. Most unexpected. And then when you continue the math out, that results in a smaller radius value of 6.27 million meters. So putting this into perspective, when starting with the sun directly overhead and traveling 5,400 nautical miles, or 90 degrees longitude, the sun drops down to 0 degrees. For the moon, however, we only have to travel 5,300 nautical miles, which equates to 88.7 degrees longitude, for the moon to drop down to 0 degrees. Putting it another way, if we see the sun as if it is traveling along a celestial sphere with the radius of the Earth, then we see the moon traveling along a similarly slightly smaller celestial sphere. And that's what we're showing here with a side view of where the sun and moon appear as the observer increases the ground distance. So the scale is millions of meters in both directions. And with the sun, it's at the 6.3 million meters, the moon's 6.27. And then if we multiply by pi over 2, we get the base radius, which is 10 million meters for the sun and 9.8 million meters for the moon. So now that we have that background out of the way, we can actually analyze the data. And you can see here the path of the center of totality spanning across the US. And the data for the eclipse path is available as a Google Earth KML file from this NASA website. It tells us precisely where the center of the eclipse shadow is cast at a given time. there are 6,770 data points at 1-second intervals spanning from 6 p.m. to 7:45 p.m. for 112 total minutes. Next, the latitude-longitude coordinates for the ground positions of the sun and moon are needed over that time span. I wrote a Python script to extract this information using the AstroPy module. This allows us to calculate the distance along the ground from the observer at the eclipse shadow to both the sun and moon positions, giving us a base distance of our triangle. I also extracted the altitude measured in degrees of the sun and moon above the horizon for the observer, but these are for reference only. They represent an optical position in the sky, and we need to use the true physical position. The final measurement needed is the height of the object doing the occluding, which in this case is the height of the moon. What we're going to do is assume the moon is fixed at the 6.27 million meter height we found earlier, and assume it is only an optical effect that causes the apparent position of the moon to drop in the sky as we get farther and farther away from it. The following table summarizes the known and unknown parameters. So first we have the center of the eclipse shadow, latitude and longitude, which we got from the data file from NASA. Then comes the observer elevation height, where we can take those lat-long coordinates and upload them to gpsvisualizer.com, which will export as CSV with the elevation data. Then the sun and moon ground position, latitude and longitude, which is generated in Python. We have the ground distance from observer to sun and moon, which is calculated using Haversine from those latitude and longitude coordinates. The height of the sun and moon is what we looked at earlier, and we're going to assume a fixed height over the observation period of 112 minutes. There's the observer angle to the sun and moon, which is generated in Python, but we're not going to use it because it is the apparent position. And then finally, the physical occluded angle from observer to sun and moon, which we don't know, but we can solve using basic trigonometry. Our assumptions are as follows. Number one, the sun and moon are at different fixed heights as they travel east to west. We'll consider any change in height negligible over the 112-minute observation window. Number two, assume the physical positions of the sun and moon are in a direct alignment with the position of the observer. That is, drawing a straight line from the observer to the physical location of the sun is going to intersect the physical location of the moon. Third, the light from the sun to the moon, and likewise the shadow from the moon to the observer, is going to follow a straight path, where refractive effects of the light are negligible. Since we're using physical and not optical positions for the sun and moon, optical effects do not apply. And lastly, no corrections are going to be accounted for ground curvature. And here are the objectives of the analysis. Celestial theodolite calculations generally involve calculating the height of the mountain peak using a triangle of the physical geometry and then comparing to the known height in order to evaluate the measure of success. Lacking certain key measurement values forces a different tactic for this analysis. In this case, over 6,000 data points are available to analyze, so instead, success will be measured in regard to consistency across the full dataset. We don't know what the height should be, but can we consistently calculate the same height across all the data points? These 6,000 data points aren't simply a similar measurement taken over and over again. Since the sun and moon are moving in the opposite direction as the eclipse shadow, the distance is constantly increasing from 2.6 million meters to 7.7 million meters, which is an increase by a factor of 3. Likewise, the altitude angle from the observer to moon drastically changes as well, going from 70 degrees down to 19 degrees, a change of 51 degrees. And then the azimuth to the moon sweeps out 140 degrees. The observer latitude changes 30 degrees, and the observer longitude changes 60 degrees. The observer elevation is fairly consistent except for this mountain range over Mexico. So the key parameters vary quite a bit over the dataset. Now let's get into the actual analysis. The first step is we're going to assume the height of the moon is fixed at the 6.27 million meters number we found in section 2. H moon equals 6.274 million meters. Step 2, calculate the occlusion angle using a right triangle where the base is equal to the ground distance from the observer to the moon and where the height is the moon height. So the occlusion angle becomes the arctangent of the height of the moon divided by the distance. Step 3, we're going to make another right triangle from the observer to the sun, using the same occlusion angle from step 2. And since in a solar eclipse the sun and moon are lined up with each other to cast a shadow on the observer, we can assume the angle from the observer to the moon is the same as the angle from the observer to the sun. So now we're solving for the height of the sun, where our equation is height of the sun equals distance of the sun times tangent of that occlusion angle. And that's all there is to it. So now we just have to perform this calculation for all 6,700 data points and then calculate average and standard deviation values. The average comes out to 6,374,000 meters, which is very close to the 6,371,000 for the Earth radius. And then the standard deviation comes out to 6,200 meters, which is less than 0.1% of the average, which indicates the data is highly consistent. This is showing the height of the sun plotted out for all 6,000 data points, and the result is very flat. This is versus time. We can also show it versus distance. And the key point to consider here is we're actually starting the eclipse here, and the distance gets smaller and then gets bigger, so it's actually going over itself exactly, and it's so perfect you can't see it. So if you're thinking the reason it looks so flat is because the amount of globe curvature at the scale is negligible, then let's take a look. It most definitely is significant. What you can see here is 4 million meters at the end, which would be very significant compared to the 6 million meters of the sun height. And since we didn't have to account for it in the calculations, that is very telling. And then lastly, let's look at the physical angle versus apparent angle. There's a discrepancy between the physical angle that we calculated and the observed angle given by stellarium, even when it does not include refraction corrections. This disparity is shown below, which increases the lower the angle gets, similar to what we saw with the profiles of the celestial sphere. The sun and moon appear to be lower than their true physical position on account of optical influences. Here we can see the physical location of the moon is at 40 degrees, but the apparent is at 20. So there's a pretty big disparity there. And here's a spreadsheet showing the data. You've got the eclipse path, the sun, latitude, longitude, and distance calculations. Same for the moon. And then here's where I calculated the sun height. So you can see there's just a lot of data points here. And then you've got the average and standard deviation. So in conclusion, the relationship between the sun and moon during the total solar eclipse can be modeled out with very basic trigonometry while maintaining good consistency for the duration of the event. It is not necessary to make any corrections for ground curvature, nor to correct for refractive events diverting the path of the sun's light. This study does demonstrate that there is a difference in the physical position of where the sun and moon actually are located versus the apparent position of where we think that we are seeing them due to optical effects. Even the globe model agrees on this point. This raises the question, is the ground beneath our feet curving, or is it the sky that appears to curve due to the nature of how our eyes perceive it, notably with the same radius value at which the Earth supposedly curves? I leave it as an exercise to the viewer to draw their own conclusions, but this only scratches the surface, and there's so much more to explore. And then let's briefly go over some things I have here in the appendix. So if you're wondering about moon height over time, here it is mapped out for 2 months, with the eclipse happening here at April 8th, and it is changing by about 10,000 meters over that duration. If we zoom into the period of the actual eclipse, you can see it's going from 535 to 570, so it's less than 40 meters change, so not very significant. And when I plug the numbers in with the varying moon height, the average number for the sun height only decreases by 1 meter, and the standard deviation decreases by 10 meters, so it's not that significant of a change.
It's wild.
And then earlier we were talking about the 88.7 degree longitude change for the moon to go directly overhead to drop down to 0 degrees. So here we have an observer directly under the moon at point A, and then at point B is that 88.7 degree longitude difference showing what it would look like on the globe model. And since we have a right triangle here at point B, it's just a matter of taking the cosine of the adjacent divided by the hypotenuse. So you can see the math here, and it comes out to 275 million meters. Now we're told that the moon is 350 to 400 million meters here in this range, and what we're getting falls a bit short. And then lastly, you might be wondering how you could solve this same process on the globe.
The guys in 24/7 are really stupid.
And it's very similar, but you have different triangles. And then in this case, you're actually accounting for the Earth curvature.
Sorry, lads, we're watching a video right now. It's not the time to talk about that. But feel free to join in the video. We're almost at the end here, and then Brian can answer questions.
But the problem occurs when you have any triangle, the sum of its 3 sides has to equal 180 degrees exactly. And so if I assume the minimum distance to the moon of 350 million meters, what happens is this distance to the sun angle and the observer angle, those two alone add up to more than 180 degrees, so it's not possible to make a valid triangle, and it doesn't work. So I hope you enjoyed this presentation. I'm sure there'll be more discussion in the future. Thank you.
Yay.
Fantastic, Prezie, Brian. Now, if anyone would like that data or the spreadsheets that were used in that, if you search Celestial Theodolite Update, it'll be update number 23. So if you click on that, it'll take you to the uploaded Excels for that, and then also a link to the PDF version of what was just transcribed there. So everything that he just read off one-to-one is also in a PDF here on the Obsidian for the Celestial Theodolite under the Eclipse section. So definitely check that out.
That is awesome, Alan. Thanks for doing that, man. That's amazing to have that all available for everyone.
Oh yeah, dude, no worries, no worries. And then there was also some guy in the YouTube comments took it, he shot his shot at trying to refute what was being put down. So Brian graciously took some time out to answer everything that guy had in the YouTube comments. So if you go here and this guy, For Clay, whatever this guy is, this For Clay guy, he had a bunch of questions and comments in regards. So he went through and answered all of these. Some of them are kind of like, not worth reading really, but anyway, you could go through and read all of these to get answers to some of the questions that were put forward in there. But yeah, it'll be interesting to see what the globularist proponents put forward, because as you went through the analysis, Brian, you stated that you weren't going to make any allowances for curvature. You were just going to analyze everything as is with the angles, and what you were getting consistently was that the sun and moon, the path of them traveling above us is always parallel to the ground, and at no point is it deviating due to going around a ball. Is that right? Let me make sure you got permissions to speak here.
That's fine.
Oh, yep, you're good.
Yeah, that's correct.
I mean, the globe protects constantly above the Earth too, so. fairly constant at least.
I do have a question. What's the entire point of doing this presentation, trying to show how much it matches with the flat Earth, and then just throwing in the admission that it doesn't actually match, and you have a mismatch between the physical location and the optical location, and you just don't know why? If the entire point was how accurate this is, then what's the point of like pointing out that it isn't accurate at the end?
So there was a sentence I didn't read at the very end, saying it probably would work with refraction, but I didn't want to take the time to do it, because if you just crank the refraction knob until it works, I'm sure it would work.
I mean, you cannot just crank up refraction how much you want. You have to actually derive it from, physical values, physical refraction coefficients. Different materials have, the air has a specific one, the glass has a specific one, and we happen to be surrounded by the air, so we have to use the one for the air, right?
Well, I'll tell you what, I posted all my data. Feel free to do the calculations yourself, but it was more effort than I cared to invest into it.
Okay.
Want me to tag you, Embo? I'll tag you.
Yeah.
And also just do a... Oh, sorry, go ahead.
Oh, sorry. No, you're good. Go ahead. You were first.
Yeah, I was just going to say, to say that you have to actually have, something physical to be derived for the refraction calculations. You can't just arbitrarily, add them in. Well, that's not necessarily true, right? It's basically a curve fit formula, and depending on the angle, it gives you the coefficient because, they treat the air, they don't treat the air as dynamic, right, as it is in reality. So there's that.
But that has nothing to do with what he was saying, though, right? He plotted the sun height as level with a level plane. That's what he used the cell Theo to do. So that question about refraction was just nonsense in the first place, but interesting nonetheless.
Right.
I was going to say real quick on top of that, the physical process of the occlusion is what causes the occlusion anyway. And as noted here, everything was plotted using the true position. So using things that affect opticals like that wouldn't be appropriate for the analysis anyway. So like if you would like to do your own though for the apparent position, that's totally up to you.
But the path
for you to do it.
But the path of the eclipse is a result of the optical location, right? Because it's a matter of light being blocked by the moon from the observer's perspective. So you could place the physical position of sun and the moon in an infinite number of random places you would just randomly select, and for every one of those places you could crank up refraction the perfect value to give you the same results as predicted on the globe. But that doesn't mean you made it work on a flat Earth. That just means that you observed a mismatch between flat and reality, and then you calculate how much magical refraction you cannot explain. You would have to add to this to make it work. It just doesn't work.
I don't know if that's an actual refutation there, brother.
No, you just talked about refraction some more.
Yeah, and also you have a gross misunderstanding of what happened there. It was plotted parallel to the ground. Over that distance, there would be 4 million meters of curvature. As you were saying, with plotted to the observer, the elevation changes over those distances, would have to show up if the ground curvature was real. The only way it wouldn't is if it was parallel to the ground and the curvature was apparent based on optics.
I mean, like orbits normally, like taking a simple circular orbit, it stays the same height above the ground even as the ground curves because you're spinning as well.
And at what point does it get lower in the horizon?
Are you talking about height above the ground or angles? Those are pretty different.
Well,
there's a drop on it.
What we're showing here is that even with the angle change, the elevation is still showing up to be the 3959. So it's still traveling parallel to the ground, even though the angle that it's being observed at is different for the observers.
I mean, like using globe model for a second, the height of the sun above the Earth is about 150 million clicks at any given time. Even as the Earth spins, even as it goes below your feet as the Earth spins around, it's still the same height above its ground position on the Earth.
I mean, using 150 million clicks is using something outside of the parameters of the latitude-longitude system itself, and actually extending it beyond the radius itself actually doesn't really affect it at all. We had used to a simulator version of that anyway, so it doesn't change anything at all past 6210 anyway.
I'm just saying that's what the globe predicts, and like it being the same height above the Earth does not imply the Earth is flat. That's what you'd expect in either model. Actually, I think it works better in the globe because I can't see how the sun would ever set if it's a constant above a flat Earth.
I mean, that's basically like saying that they predict the stars are always above the horizon. Like, that doesn't even make sense.
I mean, not above the horizon because the angles change as the spin happens, but...
Are you saying the curvature of the Earth wouldn't be apparent in the sun's path ever? Is that what you're saying? It's impossible to tell?
Well, no, I mean, you'd tell because it goes around at a constant angular rate and goes below your feet and above your head. Like,
well, we can tell that we didn't account for it and it matched perfectly. All observations actually show, based on the data in the graph that you probably haven't looked at yet, that it's perfectly above a level plane. So your assertion that it doesn't prove the shape of the Earth would probably indicate you haven't looked at the problem, right? Or the data presented.
My assertion is I just looked out my window and it's black.
Okay.
I mean, like that's
what?
It's pretty basic.
That's what I figured. So
yeah, hold on 1 second, dog. Yeah, dude, that's we're not doing like I just looked out my window and it's black type stuff. That's That's bottom of the
Okay,
barrel.
it's a
dog.
simple
So
disproof
we
of
just
this
went over a whole
unmade
data set,
concept of
and the
water.
globe doesn't predict that at all. There's 4 million meters of drop. If you're saying that there's no 4 million meters of drop, and it just happens to also look like it's parallel to the ground at all times,
Yeah,
then
that is what he's saying. He's like, well, you would never be able to tell from Earth that it's obviously it's over perfect.
listen, as we're deriving it from occlusion angles, keep in mind, right? As we're deriving it from the occlusion, like my dude moved 69 miles per degree, and then averaged out a rise over run slope, independently derived the altitude of the moon based on the said rise over run slope, right?
Well, I'm just going to point out.
So you know how our argument for years. Hold on one second, dog. Because we're
a circle, not a flat plane.
dude, the constant thing over a circle doesn't even hold up over every degree. It's only in a certain section.
Well, if it doesn't work, then why are you assuming it?
Oh my god, dude.
You're bringing up different points, dude. You're bringing up day and night, and then the path. Those are separate. Because go ahead, Alan.
Bringing up separate things and interrupting me in the middle of what I'm trying to say. So as we continue, as we've been saying, though, our point is that there's an optical equivalence between the radius value that's used in the coordinate system, and everyone says, no, it has to be the physical Earth value. Well, if that were true, then the elevation over time, over distance, would change, as it does with all the other celestial bodies that we do celestial theodolite with. What he shows is that it's parallel to the ground at all times, and it's following, when he plots it out over that arc, it's following the like the apparent positions following the celestial sphere arc. And when you do that, and you can also, what we haven't got to yet, is he also plots that for the celestial theodolite observations. So he does all the mountain peaks and plots that over the same thing, and it maps out very closely to the celestial sphere model there, which only goes parallel to the ground. Like he does a whole thing using the ground distance GP times the peak angle over the distance to the peak to get the altitude of the stars. And when you plot that out, it comes out parallel to the ground as well. Like if you're saying that there's no curvature and it just looks that way, then you don't have a position. And like this is about trying to refute the null hypothesis, not say that there's not turn it into some weird thing where you don't have a pure prediction that's mutually exclusive from ours. But anyway, go ahead and continue. Feel free to respond, and then we're gonna take questions from other people. And I have a couple of questions for Brian, myself.
The only comment, well, I don't know, what Alsadius, is that were you going to respond, or is that how you pronounce
No,
it?
I just said I don't want to monopolize. If anyone else wants to jump in, then feel free.
Well, I was just going to say briefly on that last topic. The thing is you were talking about the rotation and all that on a sphere, but that's the whole thing. The rotation of the sphere essentially is the curvature. You know, on a sphere that is curving, if you were on the surface of said sphere and it's spinning, then you're on the curvature rate, the 8 inches per mile, basically. You know, and that is what is not appearing in the actual what he presented, like the actual drop that would occur because the fact that you are on a curved surface, that you yourself are actually moving at that curved rate on a sphere in relation to the angles. So that's why I think you'd have to address that directly if you were going to.
Well, you'd address it in the end, and what I would say to that is, how do you know if the ground's curving or if the sky's curving?
Yeah, and I wanted to ask you, so bro, that was amazing, dude. I'm gonna watch that again. That was excellent. That was awesome. So kudos, and that's just cheers. That's amazing work that you're doing there. I just wanted to ask, like, could you tell us a little bit more how you think like the 3959, 3,959 mile, the claimed radius of the globe Earth, and the 6210, which is the claimed arc distance from the equator to the North Pole, and how those numbers, how the 3959 and the 6210 work into this, and what your thoughts are on that?
3959 is in miles?
Yeah,
is that correct?
That's
so the 6.3 millimeters.
Exactly. Yeah. Yep. That's the.
Yeah. So basically, if you have a celestial sphere, can you scroll down, Ellen, to the last? Yeah. Can you zoom in on that?
Get some visuals in chat too.
Yeah. So 3959 is just the height of that celestial sphere, and then as you get farther away from it, it curves down towards the ground by optics, making it appear to set. And then when applied to the stars, which you can see are the orange points, you can see they trail off because they're lingering, kind of like they're receding into the distance rather than actually going around ball curve.
Yeah, and those are so the 3959 you're saying stays a radius as it arcs down optically? It stays the same distance, the 3959?
Well, no, it actually increases to about 10 million. I don't know what that is in miles, but that's like factor 1.8 or something.
What about like how you can see like the other 6210 number? So from the equator to the North Pole on the globe is claimed to be 6210, 6,210 miles. So the fact that like Polaris sets when you get to the equator, do you think that the distance is actually 4,000, like this 4,000 mile, or the in terms of when it sets, or you're saying a little bit more? Or
yeah, I was wondering about the
6210. So you can see Polaris from the equator kind of thing. So yeah, what are your thoughts on that?
I was wondering about that myself. So to apply the different equatorial radius versus polar radius, that would basically mean the celestial sphere has a different radius depending if you're looking east-west versus north-south. So it'd be interesting to come up with an experiment that could prove that one way or another.
Yeah. So like when the sun is setting, how many in miles away do you think it is? Is it that 3959 setting, or is it the 6210 when it sets?
So if you scroll back down to the bottom picture, Alan. So what I'd say is the path of the sun starts at that 6.3 million at the top, and then it's just going straight across. But then you see it appear on the blue line.
Okay, so optically, yeah. And then so that's the globe right there. It's the optical. You're saying it's not that we're on a globe, but a globe essentially is that curve of the optics. Now, why does it do that curved optics? Is that what you're saying? Like, why is that? You have any thoughts as to why it's doing that, essentially?
Shane has talked about that related to like the aperture of the eyes and that sort of thing.
Yeah, like curved visual space. We have a radius of vision that creates this whole hemisphere that's been used to create a celestial sphere model.
Have you seen this? Can you see can you see where we're at in the chat? The live stream on text. I'll tag you in it. Llamazing. That's a great name. So Gleam made this, and it shows the 1 degree per 69 mile within like a planar matrix. And I just thought you'd find it interesting because that it shows the curve there. Now that's kind of the inverted curve, but when you actually map those out, again, it's the curve is in the visual space. Now that one kind of shows an upper curve, and that might be part of the field as well. There might be the both the one you're showing and this one, or how these intersect. But yeah, I just thought you may find that interesting. How it kind of shows how the visual space is what's actually curved, not the actual plotting on the planar ground or the vertical, the horizontal or vertical.
The old optical curve mistaken for Earth curvature. Classic rookie mistake.
Yeah, classic mistake, completely baseless made-up physics that has no demonstrations in a lab compared to just deriving angle relationships from just what kind of relationships spheres tend to have. Like you can test this with any sphere, that when you move a camera on like a basketball, it will have a linear relationship to angles to surrounding things.
That's much too long to be a quit, bro. You gotta work on that.
That was supposed to be rebuttal, right?
No, I didn't hear most of it, to be honest.
Okay.
Yeah, you were kind of mumbling a lot.
I have a quick question.
Go ahead. What's up?
I tried modeling out how to. Okay, so if we have the Gleason map, I tried modeling out how, like, say I have a celestial sphere over the planar Earth. I wasn't able to get the southern celestial sphere stars to project for the southern observers. Does that make sense before I move to the next part? Does that what I just said make sense?
Does what you're saying have anything to do with what Llamazing presented or the celestial theodolite in any way?
Okay, well, I can ask at a later time. Sorry.
No worries,
I'll just say that all the data I have is in the north, but it would be interesting to look at southern data.
Southern eclipses next update, Brian?
Can someone like explain what's the problem for this on the globe? Because the graph you have right now on the screen, it just shows a linear relationship between an angle and the distance to the ground position, and this is exactly what we would predict on the globe, assuming that the distance to the object like the sun or a star is very, very far, that it can be assumed as infinite for all practical purposes, and this is basically what's demonstrated here.
So the problem with the globe is if you map out the triangles and don't account for any refraction, the angles don't make you don't get valid triangles. So now if you did include refraction, you probably could make it work, but I haven't done that.
So was the problem if refraction does exist in reality and you didn't account for it? Like, okay, you didn't have time, you didn't want to, but in that case, why would you even present this at all? Just admitting that you didn't account for an important factor if this has no bearing in reality where this factor exists.
So the beauty of what I've done here is I've done these calculations with absolutely zero correction factors and gotten an extremely low standard deviation, less than 0.1%. So if you want to do correction factors for refraction, it's just hard to know exactly what it should be. It becomes very subjective. So I didn't see that as a valuable exercise.
Yeah, because Embo, you can just make Earth a ball that way if you want. You know what I'm saying? Like if you can get raw, trig, and planar, and you can get that consistently with a very accurate range of deviation in terms of accuracy, then that is a base reality that's being directly observed. Now, if you're going to add theories about refraction, especially if you're not even measuring exactly how the light is actually traveling, you're just going to make all kinds of theories. You could turn it into a ball, but you don't need it, even in the first place. And to think that like everything is being warped to actually make everything be on a baseline planar, but then somehow actually be spherical, really doesn't make sense compared to on the opposite side that it is planar, and that's why the actual timing and getting down to the actual positions that they're in is planar, and then you would have to add refraction to basically explain why it doesn't fit that, and then add the refraction to curve around a sphere essentially.
He literally added an unknown, unexplainable factor that transformed those coordinates into a sphere to make it look like a ball. And you're accusing me of wanting a baseless correction to make it work on my model. The only thing I'm requesting is a slight correction that is consistent with the known laws of optics that you can just measure in the lab. What he did is basically just reverse engineering the result that you would expect on a sphere, and then like doing a mental exercise. What kind of transformations would I need to make it look to make it work on a plane without actually caring if those transformations are possible in reality according to
which one of these equations? Which one of these equations is the transformation? Real quick before we continue, can you point that out? Just which one of these is the transformation? Go ahead.
The one where it lowers the physical height of an object based on the distance to its GP.
Which one? Can I send you the PDF? Send me a screenshot of what you're talking about. What specifically are you talking about?
He's not. I think what he's some shit he made up.
What he's taking issue with is the Haversine formula. And if you understand how latitude and longitude was created in the first place, they take angles to Polaris and they're relating to that to the ground position. So it's really just Haversine is mapping the curvature of the sky.
I'd still like to know what it means south of the equator, because there ain't no angle to Polaris down there.
Yeah, but you would have an angle. You can, even though there's claimed to be Sigma Octantis, a star there, but you can use the pointer stars and the southern crux to basically create a cross section, and then you can use that as the center. So you can take elevation angles from the south rotation as well by doing it that way. You may not have like a stars as poignant as Polaris is, but if you use the pointer stars and the southern crux and you take the angles of those, you can.
Yeah, that works perfectly well. It just doesn't make much sense in flat Earth.
Also, kind of a separate topic though. But yeah, go ahead.
Taking away drop due to perspective and adding the dip angle with refraction. It's a clever way, right? That way you can't refute it. Can't prove it either way. It's why the stars have to be so far away, because there's no perspective drop due to perspective. Right. It's all dip angle.
Yeah, and they see it's like they invoke the parallel and planar geometry by claiming the stars are infinite distance away to where they're hitting the light parallel, and then make the Earth curved instead of the actual ground being the parallel, the planar, and then the sky actually having these curved features.
But those two things are equivalent and equal, right? And we're here arguing about them all day long, essentially.
All day, every day. That's the beauty of the celestial theody, because we do our predictions based off of the physical source, so-called, of these of what created this model, because everything was derived off of zenith measurements and then calculating when it would, how long it took to return to that position. So using that true position, that calculated position, to predict occlusion timings has been a great tool in differentiating between whether or not the stars are actually going beneath your feet or whether or not they're parallel to the ground at all times.
Yeah, and to be clear, what our boy did here was like, oh, look at you guys using star occlusions to make actual predictions in the real world. I wonder how I can use that. And he went, oh, you know what happens? Well, an eclipse was when, the moon eclipses the sun, and that's actually an occlusion. I wonder if I can do the same trig to plot out the path of the celestial objects. And that's exactly what his data and all his graphs show. And I did see critiques to the color of the graph, the white space in the graph, the direction of the arrow. No objection to the actual conclusion or the content itself, or what the implication of the graph would suggest, meaning that the path of all celestial objects are in parallel above a level plane, right? That's what this shows. That's what the celestial theodolite method shows exclusively, and that's what this adapted, awesome, unique application of it also shows.
I just wanted to address something that is misinformation that was said here, which is that a flat Earth is equivalent to a globe Earth, which is the exact opposite of reality. In reality, a flat Earth has no Gaussian curvature. A globe Earth has positive Gaussian curvature, and what that basically means is that you cannot make an isometric transformation between each other, which means you cannot transfer one into another without distorting the distances and the angles between different points. The most simple fact is that you cannot make a plane out of a ball without cutting it somewhere. So there will have to be a point, in fact, a set of points, a line, a circle, whatever, depends on the transformation, where you wouldn't be able to go from one point to another anymore, because they would be on the opposite side of the flat Earth. And this is what happens with Antarctica on an A map. On the globe, you can get from one point in Antarctica to another very quickly. On the flat Earth, they are on the opposite sides of the Earth, because it doesn't loop in every direction like a globe does.
Yeah, nobody is arguing the placement of the stars is based on the spherical coordinate system. We're arguing that it's abstract based on the hemisphere that you observe. That's what it's the same either way. What Gio was saying was that it's an equivalence between parallel light and a curved Earth, or you can do with the flat Earth equivalent with perspective inducing with the change angles to Polaris. Those two observations are equivalent. Those two applications are equivalent. That's why this transformation works so well that I'll put in chat right here. This one, right? It's got both. It flips it. It's got all the angles to Polaris, then it has the curved Earth, and then the flat Earth angles. They're equivalent. They're expressions of the same observation. That's what we're saying is equivalent. I don't know what you quibbled on about. The map transformation, where we know that this is spherical coordinate system, latitude, longitude is hemisphere observed, spherical calculated, and it's abstract. What you'd have to do is tie that specifically to the curvature of the Earth in physicality, which you have to do through geodetic datums and ellipsoid models, but we all know how meridian arcs get measured, etc.
When you have a claim that goes against all of the known laws of physics, and my claim is simply an application of the laws of physics that are testable and repeatable, the burden of proof to show that the phenomenon isn't caused by your made-up explanation that has no evidence outside of just begging the question, then it's not my burden of proof to prove that, right? Because you made up your completely new set of physics.
Can you steal me on our explanation?
Yeah, your explanation is that visual space curves, and that makes the light beams curve between the source of the light and the observer that receives it, and makes objects appear at a different angle than they would geometrically according to known laws of physics. And there is no evidence for that outside of the very phenomenon you're trying to explain out, which means it's circular. Thank you.
And can I point out one problem with Shane's video too, which is that we know that
you can't, John, because we're not.
That's right. You don't want to hear from me.
Well, hold on. That was to be responded to. He put it back to Alan.
I was replying to Ibu there. No, specifically how the data was acquired and what it implies with the occlusions. What is the process by which we're deriving all this from? Because you keep saying that, you keep bringing this back to the globe and the globe this and all. Do you understand what we derive this under? The true positions versus the apparent positions? And that there should be an elevation change over distance like there is for everything else. And the fact that there's not, you can't turn around and say, oh, that's actually also just fine, blah, 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 laws of physics. What laws of physics are being violated here, bro? These are empirical observations and triangles. So Pythagoras is, hold on a second.
You asked me a question, I'm going to answer the question.
Oh, yeah, you're not going to answer it in the middle of me fucking finishing my stuff. So Pythagoras' theorem was violated earlier. We were talking about that, where when you try to plot these out on a globe, you get an angle that exceeds, or you don't get a valid triangle there. So that was violated. Like, what laws of physics do you think were violated? Go ahead.
Fermat's principle, which states that light takes the path of the least time to travel.
What?
What?
Do I have to repeat myself?
Yeah. No,
that-
don't bother. John, go ahead. What's up, buddy?
That's principle of least action. It's pretty well understood in modern physics that that's how things work. I can send you some YouTube videos if you like. It's actually pretty interesting if you want to.
Yeah, that doesn't have anything to do with the occlusion and the non-elevation change.
Just a virtue chart.
Fermat's principle describes no elevation change and it just mimicking a flat Earth. That's what it describes.
It describes why
definitely send me that, please.
refraction happens. Like that's
What's being refracted here, bro? We calculated this off of true positions. Do you guys listen in?
No,
You guys live in there. Go ahead.
Light to figure out true positions. Those beams of light are refracting. Like that's. We've been saying this since like day one. It's
No, but that's not what's happening. It's not an optical. It's not optical in the way you're thinking of it. That's the whole point.
So all I wanted to point
It's the
out
actual
is that,
positioning of the actual objects above the ground in their actual, like, in terms of the actual timing. If you know this celestial theodolite, I don't even know if you know how familiar you are with it, but when you get the actual timings, you're getting the actual, like, it's like the internal architecture of the actual system.
I know you guys assert that, but it doesn't make any sense that like all of a sudden the light magically like refracts and then doesn't refract and then refracts. Like it's based on basically the celestial theodolite is a way for you to trick yourselves into thinking you've got something.
All right, so real quick, Goose used the old method of like, calculating it through stellarium and timing it perfectly and figuring out what it was. So literally predicted the occlusion, and like other people have done this based off of these principles. We're using the physical like occlusion. In other words, the source when it intersects with the physical object, and that's what creates the object disappearing. And you're saying that like you're just saying nonsense, dude.
No, like I mean, unless you've got a vacuum tube from your house to Pikes Peak, you don't have the physical occlusion. You've got the optical occlusion. That's the only thing you can measure with light.
And
You can't measure physical occlusion with light unless you've got vacuum the whole way.
That's why we reference where the star's position was with respect to the peak, because the peak's either going to be at a lower elevation or a higher elevation, and that means when the star isn't visible for us, then that's going to be at that same corresponding elevation. That's the whole premise of it.
I mean, the occlusion happens when the mountain's visual position and the star's visual position are the same. That's
Incorrect. It happens when their physical positions intersect.
No, when their optical positions intersect. It can't be their physical positions. You have no way to measure their physical positions directly. You can only measure it optically. That's the core problem.
No way. No, it's not the core problem. Okay, it's the core problem, you say, buddy. It's the foundational principle. How could it be the core problem if other people have gone out using these principles and predicted measurements? Jesse even went out and did it under the same principles. So hold on a second, dude. You're not going to interrupt and say that your result comes out in numbers. It comes out in specific numbers that end in a mutually exclusive outcome to determine which model is correct. And in addition to that, we know how high the physical elevation of the mountain is. We can do basic trig to determine these mutually exclusive angles. So everything you're saying here is really just trying to hand wave dismiss everything, and it's like a big nuh-uh. You haven't provided anything of substance to refute the actual what's going on here. So you're saying it's nonsense. We can predict the angles. We can derive our location. We can derive distances. We can derive the elevations of the celestial sphere, which is the optical equivalence of what we've been saying the whole time. You're saying it's nonsense, dude. All the data is available. I'm just waiting for someone to show me where a mountain intersected with the ball curve. Where a star intersected with the ball curve.
My turn yet?
Yeah, we could shift to John or someone else. Well, can I just say, yeah, well, did he have a response, or Alan, did you want a response from him, or should we shift?
Oh, I mean, dude, if he can, like I spoke for a while, he can say something, but we'll move on to John after. Go ahead.
I guess I'm coming at this a little half-assed because we've been having the same arguments for months and months, and like I'm seeing even the same memes getting used as when I was last paying attention to this a couple months ago. It just feels a little bit like we're going around in circles. So I'll admit I'm half-assing this a little bit, and that probably isn't fair to anyone who is giving it their full ass. So if anyone,
that's preposterous. You're judging the success of the celestial theodolite based on repetitions of memes.
It's the actual positioning of the actual objects above the ground in their actual, like, in terms of the actual timing. I mean, the celestial theodolite is? I don't even know if you know how familiar you are with it, but when you get the actual timings, you're getting the actual, like, it's like the internal architecture of the actual system.
I know you guys assert that, but it doesn't make any sense that like all of a sudden the light magically like refracts and then doesn't refract and then refracts. Like it's based on basically the celestial theodolite is a way for you to trick yourselves into thinking you've got something.
All right, so
Great.
so real quick, Goose used the old method of like, calculating it through stellarium and timing it perfectly and figuring out what it was. So literally predicted the occlusion, and like other people have done this based off of these principles. We're using the physical like occlusion. In other words, the source when it intersects with the physical object, and that's what creates the object disappearing. And you're saying that, like, you're just saying nonsense, dude.
Unless you've got a vacuum tube from your house to Pikes Peak, you don't have the physical occlusion. You've got the optical occlusion. That's the only thing you can measure with light. You
and
can't measure physical occlusion with light unless you've got vacuum the whole way.
That's why we reference where the star's position was with respect to the peak, because the peak's either going to be at a lower elevation or a higher elevation. And that means when the
The whole
star isn't
premise, yeah.
visible for us, then that's going to be at that same corresponding elevation. That's the whole premise of it.
I mean, the occlusion happens when the mountain's visual position and the star's visual position are the same. That's
Incorrect. It
definition.
happens when their physical positions intersect.
No, when their optical positions intersect. It can't be their physical positions. You have no way to measure their physical positions directly. You can only measure it optically. That's the core problem with the whole
Oh, no
celestial
way.
model.
No,
I'm
it's
arguing
not
about
the
this
core
for 6
problem.
months.
Okay, it's the core problem, you say, buddy. It's the foundational principle. How could it be the core problem if other people have gone out under using these principles and predicted measurements? Jesse even went out and did it under the same principles. So, so
method will result in numbers.
So hold on a second. Dude, you're not going to interrupt and say that your result
Sorry.
comes out in numbers. It comes out in specific numbers that end in a mutually exclusive outcome to determine which model is correct. And in addition to that, we know how high the physical elevation of the mountain is. We can do basic trig to determine these mutually exclusive angles. So everything you're saying here is really just trying to hand wave dismiss everything, and it's like a big nuh-uh. You haven't provided anything of substance to refute the actual what's going on here. So you're saying it's nonsense, but we can predict the angles, we can derive our location, we can derive distances, we can derive the elevations of the celestial sphere, which is the optical equivalence of what we've been saying the whole time. You're saying it's nonsense, dude. All the data is available. I'm just waiting for someone to show me where a mountain intersected with the ball curve. I'm sorry, where a star intersected with the ball curve.
My turn yet?
Yeah, we could shift to John or someone else. Well, can I just say, yeah. Well, did he have a response, or Alan? Did you want a response from him, or should we shift?
Oh, I mean, dude, if he can, like I spoke for a while, he can say something, but we'll move on to John after. Go ahead.
I guess I admit I'm coming at this a little half-assed because we've been having the same arguments for months and months. And I'm seeing even the same memes getting used as when I was last paying attention to this a couple months ago. It just feels a little bit like we're, going around in circles. So I'll admit I'm half-assing this a little bit, and that probably isn't fair to anyone who is giving it their full ass. So if anyone,
that's preposterous. You're judging the success of the celestial theodolite based on repetitions of memes and fucking chat.
Well,
we just shown up with a brand new application of the celestial theodolite that shows that the path of the celestial bodies is parallel to the ground. Yeah, dude, we're gonna go ahead and move on to John. Thank you for participating.
Well, and can I actually interject in between though before you go, John? Let me just say,
go ahead.
Yeah, I want to. So, just real quick, just kind of on more of like a chill mode of something to say real quick. So, using the sun and the moon, is that essentially equivalent to the star and the peak of the mountain? Like instead of using the peak and the star, you're using the sun and the moon, essentially?
Yes.
So
he's deriving
Llamazing was
the
doing,
elevation. Yeah, so he derives the elevation of the moon, or mountain peak equivalent based off of the change in latitude, based off of moving 60 nautical miles per degree, and then averaging out that for the rise of a run to the slope for that to get the altitude of the moon, and then, which he uses as the mountain peak. So yes, exactly that. And then if we
so I know that's like just the basics of it, and it's like I knew that. I wasn't saying it to ask it and as if I didn't know it, because I just wanted to kind of like almost steel man it and reiterate it to kind of just give, because there's been a little bit of debating. I just kind of want to go back to a little bit of what this is on the larger, because I mean Shane had mentioned it and folks have mentioned it, but because to kind of get into just trying to debate certain things, but I mean this, he was just saying going around in circles, but I would say it's the opposite of that. This is a completely an expanded circle in a sense, if you want to call it a circle still, but it's an expansion.
Right.
Yeah.
we come with like new analysis every week, and
and this opens up, like, I mean, for example, what about Venus transits on the sun? This could be done for. Could it be done for that too? Even though that's like a smaller event.
I feel like there could be some sort of application for that.
How about ISS moon transits? Or whatever they call the ISS. We use it for that.
Ooh, dude, we gotta get with Piezo. Piezo's done some hefty work on doing trig with the ISS, and it does not look good for the globe.
Yeah, that could be another interesting application. So yeah, no, if you want to shift to John, I just wanted to sort of say that overall, because I wanted to give Brian, kudos for this. This is amazing, dude. It's such a good idea, and there's so many additional applications that this can be, can be expanded towards as well. Now, just one last thought on it. Does it essentially assume that the sun and the moon are physical objects?
No, I don't. I don't make an assumption as to whether they're physical or not. Just their location.
They're lined up. They're just lined up. Like the circle we call the sun, the circle we call the moon, the actual angular amount it takes up in arc minutes and angle in the sky are just in the same position. But you don't. It doesn't necessarily have to assume that they are spheres or they are something else or they're lenses or any other additional. That would all be sort of additional components.
Correct.
Yeah, one thing specifically that we're not claiming is that these are the true altitudes of the celestial bodies. This is just what the trig comes out to based off of the celestial bodies and the occlusion timings and whatnot. So this is a conceptual model, and what we're putting forward is that this lines up with the light source of the celestial bodies. If you could consider, like a flashlight that's moving, like when it's moving fast and far away, it's gonna lead the apparent position of what you see by a little bit. So like we're saying, over the distances and all that there's some source of light and that's being intersected by terrestrial features, or in this case, the moon, which does imply a physical situation, but we don't attribute any actual physical altitude to it. This is all conceptual model calculations substantiated based off of real world occlusions.
Yeah, the celestial theodolite.
Yeah.
Sorry.
Go ahead. Okay.
I was going to say the celestial theodolite just shows that the stars are parallel above a plane of Earth, and Brian showed that the sun and the moon are also in the exact same way parallel above a plane of Earth.
They partake in the parallelism.
Yeah.
And that height above the ground is the 3959?
Yep. Close to it, yes.
So, I mean, you could say that's where the globe came from, right? That's what I've been saying forever. That's the argument. If all the celestial bodies are at that distance and then act in that way, and then the arc that you see perpetuates at that rate, then, you can definitely make the bottom of a globe out of some math, use a spherical coordinate system to represent everything, have everyone observe the same hemisphere at any given point, and nobody would ever be the wiser.
That's how they did it. And then they also had to space them out and make them all like balls surrounding the ball. And when you do that, then you have to put them in certain distances to kind of equate for their time, which is just like an inverted mathematics. But yeah, that's how they pulled it off.
Yep. And then you mark down, you make the actual map, you mark out the celestial sphere, and you make that a true position, reference epoch, and off everyone goes, referencing the same star position and across the whole plane.
Can I ask a question? Just me at the
Question,
bottom
actually.
down here.
On something that is
I
a
don't know
little
if
more.
John still wanted to go or he's not here still. Did he leave?
Just quickly, the moon and the sun in that model that were discussed tonight, they were both almost exactly 6371 clicks above the ground, right?
Yes.
So in the case of an eclipse, like, were they exactly the same height, or was there like a little bit of difference between them? Like, how close were they?
I believe the ratio is 1.016.
Okay, so within 1%, so within like 60 clicks. Okay. Yeah, I guess I was just thinking if they're too close, then they might even run into each other in that model. But I think 1% might be enough to keep them apart.
They're effectively the same distance from us then, no?
I mean, yeah, that is what tonight's presentation was suggesting. I mean, obviously, I don't agree with it.
Absolutely. And then
That's
also,
exactly what it would
lastly,
suggest, yeah.
I'll see if I can find the link. But Goose made that awesome Desmos model where it compares the celestial sphere model on a flat Earth to the globe, and you can see that past 6210. There's like you can say that it's 93 million miles away or whatever, but after you get past 6210, nothing matters. It's the same.
It's effectively infinite, you might say.
Can I ask a quick
yeah,
question?
I would say that. Sorry, yes, go ahead.
They do,
The
yeah.
6210 also fits to like the way they say the ball. It's a ball, and you can only you're on half of it, and it's half lit up and all that. Because the 6210, I mean, the way they claim like the circumference of the equator is around 25,000. So, 6 and 6 is 12. So it's like a time if you're seeing 6 one way, 6 the other way, or 6 all around you, then that would be like half of, well, the 12 would be half of the 24, or roughly 25 for what they claim the circumference is. So yeah, I think that's like connected to it too, which does get to like the day and night cycle as well. But yeah.
Yeah. I just both assume everyone sees half of the sky at every point. Like that's
Yeah.
the basis of it, really.
Sorry, was there a question from someone? Yes, sir. Yes, go ahead.
Yes, please. Thank you. I'm just going to ask a question. I'm not countering anything or any gotchas or anything.
I just read it. I joined. It just says join, and I thought I was joining something else. Yeah.
Sorry,
Thank
guys.
you.
Go ahead.
I'm just trying to understand the actual stars. So we have the planar surface, the actual stars, not the apparent stars. Is it a celestial sphere overhead or a star plane or?
Ooh, great question. Great
And
question.
if it's not known, that's okay. I just I was wondering if it's known. I'd like to know, and that's all I want to know.
The way that I conceptualize it is it's like a celestial disk that's above us. But I think piezo has an interpretation where it's a sphere that's projected out. So like you'd have to there's some room for some variations, but I think the South Theo implies that that it's more like a disk rather that's spinning above us or something.
Okay, I appreciate that. Thank you. That's all.
Well, and also here, I'm going to post this image real quick, which is sort of linked to this. What would you guys say of this? I posted this in the chat. It shows essentially like a flat plane of stars with a curved actual visual region, and that's the transfer, or that's the. Well, it's not really a transform or a transfer, really, but it would have to do with that relationship.
Oh, I made that one.
You made that?
Yeah.
Well, I stole it from I think the Australian guy, and then I added the arrows and the 15 degree. But this is the exact conceptualization because he was arguing that there was a flat plane, like a flat plane of stars above a flat plane of Earth, and we were like, "No, dude, it's an arc and a set. Look, it's a hemisphere above me," and it's like, "Oh, those two are the same." The celestial theodolite and this new interpretation analysis really cement that actually this is what we're looking at, right? They are flat in the parallel to the plane. But because you don't see forever and because you only see half the sky, literally as they come and go, they appear to rise and set for this dude sitting in the middle. That's exactly what it is.
And the implication here is when you have two parallel plates, what do you get? You get a capacitor. We would live inside a giant capacitor.
Yeah, so that is the new position for are the stars. They appear to curve around you, but they are in fact, I think, in a plane above the plane.
So I wanted to comment on this and be a bit more nitpicky, but I don't think this is the right time. So that's
good. Go
really
ahead.
all I wanted to know. Thank you.
No, this is specifically the time for it. Go ahead.
Oh, okay. Okay. So with that, with the idea of a celestial sphere, this is my understanding. So if there is a plane overhead, the plane Earth, all the stars at the edges of the star plane, so that would be the southern stars, right? At the edges of that star plane. Because if there's a star plane, the center of that star plane would be like Polaris, which is directly overhead the North Pole. So if that's the case, then the edges of that star plane would be the southernmost stars. And
well, the thing.
So,
yeah. Sorry. Go ahead. You're good.
Yeah. So I'm not telling you guys anything. This is my understanding, and I could be wrong. But for an observer looking at the southern stars, what they're actually looking at, let's say you're looking at the southern axis of rotation, or what appears as apparent as the southern axis of rotation, that would actually be all the stars around the edge of the star plane seen simultaneously and brought together at a single point.
Well, I think you're confusing the physical positions of them with the apparent, because the thing that makes the sphere is a conceptual model of how they just curve visually, and like as they get further away from you. So the celestial sphere is not like a real thing. It's not like they're fixed to an outer shell or whatever. That's the conceptual model that's just a version of a conceptual model that they use to describe the optic nature of what's being put forward. That's why the occlusion timing showing that there's no deviation to the true position over distance and like just really nails the coffin that there's no curvature at all. Like
Yeah,
they're
because
literally parallel to the ground. Like there can't be a different geometry for it, because if there was, the outcome would be different. For example, if the Earth was curved like a ball, then the mountains would be lower, so the stars would, when they're being occluded, they would get occluded at later times because they would still be visible because they're not intersecting with the physical object until it's lower. And if the Earth were concave, like lifting upwards, then then on the inverse of drop there would be lift, so it would get occluded at an even earlier time than what just regular plane trigonometry would predict. And the only thing that consistently is showing up is just the plane trigonometry. So it's telling us that what we perceive in the heavens is purely optical. And they're like in that image that we were looking at earlier that Geo posted, like the sphere here, this is all just based off of optics. This is an optical model. What you could do is you could, like the way that they teach it in the globe model, they say, okay, let's assume you're a fictitious observer at the center of Earth and you're looking up, and then up here is the ground of Earth, and all the stars are fixed to the ground like little orbs inside of this sphere that you're in. So because it's a direct optical equivalence. And then so what the cell, like, they would have us believe that this is like reality or whatever, but this is just how we see it, and the motion appears to be, what's going on up here. But again, we don't even know anything about up here because our limit of vision only extends to create this. So we actually have no idea what this is, but the timing in which these intersect with the ground makes it so that we can't see in this bubble anymore. So that's the relationship that we're drawing to establish the parallel to the ground. So other than that, like how to explain what we see in the south and all that kind of stuff, it's not really, we would need mountain occlusions with stars to start to kind of draw any conclusions about what happens as we get further out in the south in terms of the shape of the ground.
I got you. I would really be like interested to go into further detail whenever we like really definitively do the Southern Hemisphere stars. I don't want to take up more of you guys' time on what all we've covered. So,
Yep, no worries. Thank you.
thank you.
Well, so to have a planar like Earth foundation, like water and Earth overall having that planar foundational geometry, whatever the stars, wherever the objects are in the sky, it would make sense that they would, like in terms of the coplanar. I'm not necessarily putting forth the argument myself right now. I'm just saying it would make sense that you would have, like the way you have a GP, a ground position, a GP, and just the consistency of them, the way they're like clockwork. The way that like the Big Dipper is going to be, if you're right under the Big Dipper, like 23 hours, 56 minutes later, it's going to be right above you. And so, because if you have a planar surface, you couldn't, unless the stars were like holographic or something else where they were like appearing in, in some other way, there's really, like, there's no way that the stars could appear curved and actually link to the ground curved. You know what I'm saying? Like if the ground's planar, there would have to be an equivalent angle directly above and at every angle to it above a planar surface for it to actually work geometrically with having that. Now you could have a huge curved one, maybe like a larger curved dome or something that would have a slight curve to it, but I'm talking about the amount that we see, in our local range of vision. So like you couldn't have local range of, realm vision that were like limited that matched up for everybody, fully. If you know what I'm saying, like in that way to where it matches with the ground. But if you have them planar, if they're actually planar, then you could have consistent positions as they're moving, and then it would just be optically viewed in that way. And then you're kind of invoking the parallelity that they claim, like the parallel light rays from the globe. You're actually getting that from parallel between ground and sky, and then the actual curved realm in which you're seeing it from, and then that's what they invert into the globe.
Yep. Either the ground's curving or the sky's curving by exactly the same rate for both.
Are you saying that they wouldn't be able to establish ground position relationships relative to the lattice on a globe?
Yeah.
Uh,
Well, wait.
if
Say
their
that again. Wait.
hypothesis-
Wait. Was that a question for me? I kind of said yeah, but I stepped
Yeah,
away from. I was also go ahead.
yeah. It sounded like you said that they wouldn't be able to establish ground positions to stars in their conceptual model of the terrestrial sphere. I could be mistaken. That's what it sounded like. You said it wouldn't work for them, but it would work only if it was actually planar.
Well, yeah. I'm trying to think deeply, like on that.
I'm pretty sure it would be equivalent either way because they're just taking a zenith measurement whenever it goes overhead. So they could definitely do that.
If you assume the stars are, well, I think I was kind of linking in a few things. So like in the globe model, when they assume the stars are like, and I was kind of fumbling through my words a little bit too, so I didn't maybe say it exactly right. But well, it's like they claim the stars are all parallel because they're so far away. But like you were saying, that 3959, which they claim is the radius of the globe, going to the center of the ball to the outer edge of the ball, that's how they treat it. That's really the visual space that you see in. And they just say that beyond the 3959, it's just light years, basically. So and then the parallel. But yeah, and then I was kind of linking saying, well, if the stars actually are parallel, then over a planar surface, that would make sense. Now you have the coparallel. Instead of coplanar light rays from light years away, you're actually just having the coplanar level of stars above the coplanar ground. And then the curved part would then be how it's viewed, in the interim. So yeah. And then I was just kind of linking that to say that if it's only viewed as curved, but isn't actually, in terms of what's actually planar, then that would also make sense because like if we all have our own personal dome of vision, like do the stars actually move with us? You know what I mean? And are changing, or is it actually just optical? And in reality, they're just coplanar. So I was just kind of thinking another thing is that if you had smaller little
gotcha.
hemispheres, yeah, that wouldn't work either on a plane unless, if they have those consistent GPs and then getting to this timing and the angles of it indicates that, that looks to be the base architecture.
Yeah, I will cut in and say one thing. In the globe model, there are definitely things between 3959 and effectively infinite. Like the moon's 250,000 miles, for example. Geostationary satellites about 36,000. Things like that. There's not much in the way of big celestial objects that are easily measured from anywhere, but there are definitely things that can be measured at different heights all through the spectrum.
Yeah, I hear you. I was talking about the stars, but yeah, I mean,
stars, yeah.
Yeah, I found the video where I stole that actual animation from Mitchell from Australia. He was talking about cell nav.
Nice.
Before I added the
Shout
gay
out
stuff to it or whatever. Yeah.
Shout out to Mitchell from Australia. That was my
because he had the same
accent.
Dude, he had the same concept that it took us like 2 years and like 43 celestial theodolite observations to come to the same realization. Before this, I thought like all the stars were curved above us because that's where they appeared to be. You had to work in, curved visual space, a visual space versus a visual field, how Euclidean geometry applies to a real world. Do train tracks actually converge in real life? No. Okay, what does that mean? Oh, the stars could be just in a flat, infinite plane above us. They're not infinite, but effectively bigger than you could ever see, so that the limit of your vision put out in an arc in a radius of a predefined limit would then give you the apparent field of living under a sphere, right? Because if everywhere you go shows you the moving portion of the same hemisphere, then you'd never be able to differentiate that from living on a sphere and living on an infinite flat plane where you only see the certain amount in every direction.
I was going to say too with the if no one's going to add to that, well, I hear you on that, and that was well said. But I was going to say too, to one of the things I'll see it just said. So you do have like local like GPS lights and things where they claim are local, but they claim the moonlight is essentially hitting the Earth parallel as well. So the moon is like the closest kind of celestial thing. There's not like some man-made object or whatever. And because like doing eratosthenes between sunlight and moonlight, it should be different on a globe.
Yeah, I mean, if you get like opposite sides of the Earth and measure angles to the moon, you can get some parallax, like fairly easily measurable. But like, you need a fairly long baseline for most practical purposes. So like, you work with someone in Australia and make it happen, sure. But like, you want to be like a long way apart in order to get a baseline big enough to notice with normal household tools.
So does anyone have any actual refutations of like the actual math and observations for this in terms of the planar timing? Like, does anyone, just to bring it back to that, maybe, or does anyone have any actual refutation for it?
Solar eclipse occlusion by the moon, predicting the same celestial object path above a flat plane. Yeah, let's hear answers to that.
No, that'll be awesome. But yeah, we could definitely, this is new information, new application dropping on everyone. So we'll give it some time to marinate for the boys and disseminate to the elite globular all stars and see what they come up with next week. But next week, Shane had a really awesome idea for the format where we go over each individual measurement and go over objections and contentions to them and see what all we can agree on and what we disagree on before we move forward with each measurement and just kind of go over and reiterate. I appreciate everyone participating, and although some efforts were lesser than others, maybe next week there will be a redemption arc, and everyone loves a good redemption story. So we'll see you guys next week. If you have any questions, comments, or concerns, please highlight me and I will respond with any data or whatever you need to help you get it all figured out there. I'm going to go ahead and wrap up for the night, lads, if there's nothing further. Nothing further going once. Nothing further going twice. I'm just kidding. All right, I'll be back, lads. I'm gonna go roll the outro. What's up, Gio?
Well, no, I mean, I would just say thanks to is Brian. Is that your name, Brian? Llamazing.
Yeah.
I just want to man, dude, great work, dude. That was incredible. I really appreciate that. I was like honed in during it. I'm gonna actually watch it again to see all of it, and it's great, Alan, that you have all the documents available for everyone to look at. So, yeah, and it just, I mean, maybe as a closing thought, like, how did you come to this, or like, what was your, how did you come to this? Maybe it's just if you want to, Alan, if he wants to give maybe a closing on that, or I guess that's just what popped in my mind.
Oh yeah,
yeah. Cheers,
yeah,
and thank
absolutely.
you for all of it.
So I was talking
How did he?
I was talking to Bill in Discord chat, and he was discussing eclipses, and I just happened to have a model I made, or a picture, showing it from the 2024 eclipse, and I sent it to him, and I showed him like the sun and the moon, why it was moving west to east, and then after I sent him the DM, I was just kind of like staring at it for like, this could work celestial theodolite, so I tried it.
Right on, man. That's awesome. That's awesome. That's great to hear. Yeah, it's a really amazing application of it, and it has so many more implications in the future too, to like map out, additional celestial bodies, because there's a lot of bodies that occlude, of course, in terms of like it's often called a conjunction. So yeah, when any two bodies can join, and these effects can be had. So yeah, we could even map out like the larger system with it as well in terms of the other celestial bodies. So yeah, cheers. I just wanted to say thank you for putting that all together, and I'm gonna check it out further. And yeah, thanks again.
Appreciate it.
Cheers, man.
Oh, dude, that's such a good idea, Gio. The conjunctions. Brian, do more work on our behest.
Yeah, because there's all the other, like, you'll have like, there'll be like a Saturn Pluto conjunction, like whatever Saturn and Pluto are. I'm not saying they are balls out there, whatever, but the celestial bodies that are Saturn and Pluto,
they are sources of light. If they conjunct, we will occlude and make triangles with them.
The thing about the solar eclipse is where the shadow is, the exact location. You don't really know that with conjunctions of just random celestial bodies.
Oh, that's a good point.
Well, that's true. With the eclipse, it's really defined because you get the timing of it, and yeah, that is unique. I do hear you on that. Other ones will not be as dramatic and not as accurate too, probably.
For sure. Really nilly selfie-ing the whole sky, I guess. Okay.
Right. We're just gonna self Theo the whole thing, dude. All right, I'll be back. I'm gonna go close out.
Triangles.
Anyone else wants to put forth spreadsheets and do community projects?
Sorry, I'm going to do my outro over here too, because I'm going to promo what we're going to do for this Friday, because I'm doing a relativity Prezie on Friday here. So for Tuesday, we're going to be reading the Shanklin paper over on Ether Cosmology, and we're going to be reading the Thomas Roberts paper that supposedly refute the work of Dayton Miller, who continued the Michelson-Morley style interferometers experiments, and he used different elevations, different materials for the interferometer, different types of shielding, etc. So we'll go over what the mainstream best they could do to muster up to refute these measurements. And then Friday, I'm going to be giving a presentation at, I think it'll be at 8 p.m. Let me double check. What time is that? 10 p.m. on Friday, I'll be giving a presentation at 10 p.m. Eastern, that is. I'll be giving a presentation on the history of wave invariance, and it's titled Relativity Theory Doesn't Exist. That's a pretty big claim, and to understand what I mean by that, you have to show up to the Prezie. But if you're a relativist or know a relativist or know some relativist enthusiasts or people that think they like relativity, invite them and have them come and learn all about relativity, because as we learn about the etheric framework from which relativity is derived, we will learn about relativity itself towards the end there. So we'll learn all about the history of both paradigms. So it'll be an interesting Prezie there. So tune into that on Friday. And then this coming Sunday will be Globebusters, where Mana Stone's going to be presenting on his version of the etheric model, I think. Right?
Nice.
Thank you, guys.
All right, closed it out, lads. See you guys next week for episode 24. Thank you, Gio.
Yeah, bro. No,
for
it's amazing, dude.
for
It's good
hosting here.
stuff. Yeah, no, for sure. And dude, there's this opens up an entirely new like arena of research, observations, and more measurements. Like this, it's pretty exciting. Like there's so many directions and additional work that can be done with this in terms of when you bring in the celestials and these occlusions. And then do you think that could lead to ultimately even getting towards like a map, like an actual real map, like the correct map, because of when you get these timings and all these angles?
I think the correct map is the one we have now. It just relates ground positions to where stars once were for single observer observations tied together by, it's only tied together by the transformation to the center with the fictitious observer. So it doesn't represent anything differently than what we're saying. Like I think it's just as correct as anything else.
Dude, I'm more willing to accept the two-sphere model that Ptolemy put forward, just because it's a very convenient, uniform system, especially with all the work they put in hammering out the finest details of it today. Like trying to compete with WGS84, which inarguably is an accurate, model of the world. They just happen to shove it all into an ellipsoid. So, I mean,
they just make sea level curved. They
just literally make sea level curve by using an orthometric height conversion between ellipsoid and geodal models, so that if you were to draw it out on the whole model itself, sure it curves, but nobody ever sees it and you can't measure it, and it's only when you factor in this radius value that we'll just shove in whenever we need it, and that's what really drives the whole thing. It's all math.
Yep. It's like the radius of your vision will curve that water for sure, but nobody will ever measure that water physically deviating from being level or spilling over, or they'll never have to account for anything like that. There was two canals that were built, before globularity existed. One of them was in Korea, the other one was in China. I forget the names right now, but they're like these huge, massive canals, and they were built pre-globularity, just under the principles that water's level. And there's no curvature to be accounted for in that. So,
yeah, my new position is to embrace the model whenever possible, and then to just force them to differentiate. Okay, this beautiful, nicely working WGS84 ellipsoid model, where precisely does it tie to physical Earth being curved? We point it out, and they go, okay, well, it's a really, really gray process that's called measuring, arcs of the meridian arcs, which they do with, charades and chains over tiny portions, and then they calculate it based on astronomical latitude, and then they just perfected that with astrogeodetic surveying with GPSs and the advent of satellites, and throw in their coordinate system transforms, and boom, they have it mapped to like the millimeter of where everything is, which inarguably is accurate, right? We disagree with the model in which they represent it, but the data itself, everything that they have, You know, it's very, very accurate and it worked. We use it all the time.
Yeah, the whole flat Earth doesn't have a map argument was an invalid argument the whole time because of that.
Yeah. Yeah. It is a lot of the discussion now. How look, it can only be represented spherically, and it's like, yeah, you're just making the misunderstanding that the origin and the source is the curved spherical Earth, and that's not the source. The source of all the data, all the maps, all the worldwide projections is sure it's a spherical coordinate system, but it's an abstract coordinate system called longitude and latitude, derived solely based on angles to the stars. So now what? If that's the source of it, then how come we can't use that based on the hemisphere that everyone observes?
You just got to remind them not to conflate the celestial sphere for the Earth.
They do it all the time. Everyone does.
You bet.
Yeah. If instead of using the I lost it.
Doesn't smoke too much.
Yep.
Yep.
Well, it's just that it's derived from the sky, not the ground. It's not like they went out there and measured curve and were like, "Hey, we're on a sphere."
Wait, it's back. It's back. So if instead of using like the AE map to define your latties and longies, you just use two separate star maps for the southern and northern hemisphere, like they used to do, that would be, there would be no difference between finding like ground positions because you would have the relevant star information just displayed in a whole hemisphere instead of projected out and looking all insane. But like the equivalence is the same because that's all they did is they just merged the two hemis with their fictitious observer at the center. That's the only thing that made it like a conceptual model that gives them like a god's eye view where they're like, looking at the ball from an outside perspective and seeing stars move around it through another celestial sphere that's like outside of it or whatever. That all comes from stitching it together with that fictitious observer. But the Chinese were navigating using using like two hemisphere star maps. They had two different catalogs, so they didn't have any problems.
Like two AE maps, one for the south, one for the north.
Yeah, if you look at the picture that Shane posted, one's for the north hemisphere, the other's for the south, and they used to keep them separate. Or you could have one on the backside of the other, but like the whole merging them together as a conceptual globe comes from the fictitious observer at the center thing.
Right? At least they have the planisphere represent by latitude or your specific hemisphere, and then they have a different southern planisphere, right? And that's how they ended up with the map. I think you just map it based on the location, you stitch it together based on the fictitious observer, and that's what you get. Yeah, there you go. You do the same thing.
I just posted that one. I think that one's for 40 north, the planisphere. Yeah. Go ahead.
Yeah, and stitching it together is dependent on synchronizing time. That's why the whole story about John, what was that guy's name, Shane? The story about the chronometer and Newton and all that.
John Harrison, the best carpenter chronometer creator or whatever that ever dead live.
Yeah, that's why it's so important. And like they need like mutual exclusivity over it because the Chinese already had a chronometer. They already had an ability to have time over. Dude, how crazy is this, Gio? The Chinese had water clocks and sand clocks that they could take with them, like portable ones that they could put on ships. And then anywhere that they went, where they pulled up on land or even on the ship when it was calm enough to make the measurements, they could make shadow measurements, reference their table, find out their longitude or latitude, and they get their time of day for when it's going to be local solar noon there. So then they could establish time, calibrate all their clocks in case they're off or drifted or whatever. Just hard reset them to local solar time, and then have their exact time. Like it's, dude. Like, and so like anyway, we're told this whole idea of like. It was discovered by the Europeans on how to keep time at sea and all this stuff, but the Chinese figured it out a hell of a long time ago, and we're using it to navigate with two-star maps under the same principles. It only the globe only comes from linking it to that center observer with time, and in a lot of stories.
And they did it without in any way needing to treat the Earth as a sphere. essentially, with all those
Comple-
the angles. Timing,
completely independent of it. And in the 1600s, like in the mainstream story of how the Jesuits delivered history to us by their accounts, right? Not even coming from the Chinese, by what the Jesuits tell us, when they showed up in the 1600s and presented the two-sphere model to the Chinese rejected it and didn't accept it until like almost the early 1900s. So because everything that they had done and accomplished, prior to the Jezzy showing up, they had already navigated and mapped out everything from their history, and did worldwide expeditions and used star catalogs, and they derived everything from shadow set tables. So based off of tables that they had gathered over time, they measured the length of shadows cast by a 40-foot well, it wouldn't be 40 feet, but 40 lees, that was their unit of measurement then. So whatever 40 lees would be back then. But basically just a long pole. They would measure the shadows throughout the day, and they would create catalogs for those. And then they realized that the shadow lengths changed throughout the year. And and then also relative to the latitude. So once you got a certain distance away from the other one, there was like a noticeable change in the shadow length position. So they marked all those out, and based on the shadow length, when they set up somewhere, they could just measure the shadows, reference their tables, and then they instantly knew their
Oh, their
latitude,
latitude.
and had their time. And then to find out their longitude, what they would do is they would wait for an eclipse, and then during the eclipse, they would look up at their zenith, and they would look for any bright star in their star catalog that was transiting their zenith at that time, and they would look up where that star once was at Beijing, and then they would multiply that by their time difference that they derived earlier in the day from getting their solar noon. They multiply that by 15, and it gives them their longitude. And then they can take all that back to Beijing, and the astronomers can go to work on it. But yeah, they were hardcore flat earthers.
Dude, I'm pretty sure the Jesuits invented that, called it the globe, set it to Greenwich Mean Time, and everything you just said is a lie.
No, that's exactly what they did. And in like 2002, some guy and his team went to like 4 locations all around the world: Australia, Tahiti, New Zealand, and some other place I can't recall. But they went there during an eclipse, observed stars at their zenith, and then referenced where they were at Beijing, took their local time difference from Beijing, subtracted that from their local time, multiplied that by 15, and got their longitude. And they were accurate within within sub 1 degree, so literally within 69 miles of of accuracy. So very cool.
Yeah, dude, that's incredible, and it makes me think about. I've often said how if Earth really was a sphere, humans would have figured it out very early. Even with what you're talking about, yeah, like they would have already been like, we're on a globe. If that was the case,
They
would have been able to derive
smart.
it. Yeah,
There's a reason that all of the ancient cosmologies. Well, I don't know about all, but this is the way that I was reading it in the Chinese, the Japanese, and the Indians. So like a Hindu cosmology and stuff like that. All of those lads conceptualize what we see in reality as like fake. And then the heavens have true positions, and we'll never see the heavens because all we see is like, this fake illusory reality. And so like they understood like the basic principles of like, what we see is sometimes an illusion, visual space distinctions are in there, but they distinctly separated the heavens from the ground. And even when the Chinese started to navigate and take astronomy more seriously, their entire cosmology changed. They shifted from a flat Earth and a parallel flat Earth with stars that are parallel to them, to a flat Earth where the stars are still parallel, but there's an artificial dome imposed as a function of the limit of their vision. Like they figured it out. Like how you said if it was a globe, they would have figured it out a hell of a long time ago. Like everything that we've been arguing, the Chinese, Japanese, Hindu cosmology, they all figured this out forever ago and just describe it as like a religious spiritual metaphysical thing, but like in reality it's even well known and established that
Well, dude, that's pretty close to what we do.
There's a distinction between visual space and whatnot. So yeah, they've always known.
Yeah, like it would have been able to be derived early on just from even doing celestial navigation, but that's a whole nother topic. But yeah, but like what you're talking about, like timing, the angles, sundials, all of that. Yeah, because there would be no, like when there wasn't any original need to think of it as a globe, they just treated it as what it is, which is level, horizontal, vertical, etc., and then mapped it that way. Yeah, that's why maps are all essentially on flat tables, and then you mark out, your distances and all that. I mean, I've said this too, that if they were doing celestial navigation, if it was a sphere, they would have at some point been like, wait a minute, we have to curve this map. Like I have to make a curved table, or I have to like, get some wood and start whittling and actually make like a spherical curve to it, to have everything fit. But, and yeah, what you're talking about, going to these different locations and then, yeah, linking that with the eclipse patterns too. So yeah, it's like we're recovering or rediscovering a lot of what the ancients knew, and it's like all been clouded over by this whole globe deception and everything that's gone along with it in this kind of modern era cycle that we're in.
Yep. I think we had our own shadow tables, dude, and the Jesuits came and like stamped them out, and they were like, "Nah, you know what it is? You only know where you are because of globe, and we have this coordinate system for you." But dude, I think if you look at the history of like maritime navigation, I did a presentation on it. Super interesting. They'll tell you that we've always known it was a globe, and like because of Ptolemy and the ancients and Hipparchus and all the math that they knew, and Eratosthenes guessing this, everyone knew it was a sphere, except everyone sailed as if it was flat for like 1,600 years. Right up until there was some crashes right up before the 1600s, and the Board of Longitude got together. They were like, listen, guys, because of all this one crash, all these crashes, this one crash definitely, but could be definitely many more crashes. We need the longitude. We need to unify our method at sea. Otherwise, people are going to keep crashing, and we'll never know how to sail on the open sea. And then counter to that, you have people, in Asia who have shadow tables based on observations of the sun, and then water clocks based on telling time at night. No need for a fictitious John Harrison to come create the perfect pocket watch known as the chronometer. So now you can tell your position at sea based on the nautical almanac and the most precise time. Their whole system is based on nothing, right? It's based on the celestial navigation. So knowing where you are, comparing it to a reference epoch somewhere, whether it's Greenwich Mean Time as the Jesuits put forward for everywhere else, or Beijing Shadow Time, whatever you want to call it, as long as your tables can be correlated to that. As long as your tables can correlate to that, then everyone everywhere knows where they are. And that's what the Jesuits supposedly gave, and like gave the gift to everyone of navigation, right? That's what the whole story is. But I think it's funny that the history is all of a sudden, forever, everyone already knew it was a globe, but everyone treated it as if it was plain sailing with like regular maps and Portolian charts, which are like compass roses with grid wind rose networks and constant compass bearings. All that stuff, they used it continuously right about before 1700. So, Eratosthenes and Hipparchus in 200 BC, everyone knows it's a sphere, except no one treats it that way for 2,000 years. And then the Board of Longitude and the Jesuits come and tell us everyone needs to treat it like a sphere. Here's why. Here's what we can do. And all the Asian culture rejected it. They were like, get out of here. That's retarded. We can already tell where we are and get everywhere. We don't need that.
God bless the Jezzies is all I got out of that.
The history of how we navigate, it's so funny. It's like, if everyone knew it was a sphere, why did nobody treat it that way? And they were like, duh, because of the longitude problem. What? So for 1,700 years, everyone had the math tools, the understanding, the two-sphere model, but nobody used it. Interesting. Because whenever you look up the history of the globe, the answer is always, tis always been globe, right? That's what they say. We've always known since forever, since before recorded history, we've always known it was a globe because sticks and shadows.
We used to think it wasn't a globe, and then we realized it's always been a globe.
No, we never knew.
We forgot.
We never not thought that, but simultaneously, all the ancient cultures thought that, not that. So, whatever.
Thought that, not that. All right, lads. I'm gonna go take a little break here, see what's going on in the house. I'll tap in with you guys next Monday. Well, and then also on Friday. So if you're interested in relativity / ether, or you think the Earth's in motion and want to, talk about that, definitely show up on Friday. There's going to be an awesome presentation going over the history of ether and relativity theory.
Great session. Thank you for sharing.
Clap, clap, clap.
JT.
Yeah,
That's
Alan,
all
bro,
I'm
that was fire. That whole the last several hours, dude. It's very like, well, because there was a little break there, and then like that's coming back strong with something completely new. So that's awesome.
Dude, we had to come back hot, man. While I took a
Yeah.
little break while I was moving and stuff. I knew there was going to be a break coming up, and then so I wanted to keep the episodes coming in consistently. But yeah, we only took 2 weeks off, and we'll be back next week with an in-depth analysis that should be more viewer interactive. We'll be trying to get more engagement with the Globe Lads for disagreement and stuff, like with the actual data and not just like conceptual things like I disagree with the refraction amount that you chose or whatever was going on earlier. And shout out to Brian, dude. The fucking
Yeah, I was
what
gonna
a
say,
what a
over
G.
there.
yeah. So I was gonna ask, like, did he kind of do this on his own, and then you saw it, and then we're like, oh my, or was it a joint project at all, or?
No. So he kind of laid the groundwork for how he conceptually came up with it, but he presented it on our 2-year anniversary show. We did a community showcase for our 2-year anniversary, Ether Roundtable 104, and that was one of the prezzies that was presented on there.
You make it sound glamorous. 1 week we farmed out the Prez to all the community, and the community came forward with their awesome 10-minute to 15-minute presentations, one of which was Brian's immaculate presentation, which we then started showing everyone.
I like the way that I made it sound like
you made it sound so formal. Like,
well, what happened was we
had an artistic gallery where we created all the presents. Like,
listen,
no.
Here's what happens, Gio. We put out a call to action, right? We were like, listen, any lads enjoy it? Yeah, we put out a call to action, and the boys fucking came in hot.
My God, they did, yeah.
You were like, is there any gravy out there? It's like, yeah, they got lots of gravy, all heated up, ready to go.
Dude,
That's
did
awesome.
you see Vambi's Prezie on refraction, bro? Woo!
I think I saw a part of it, but I don't think I saw. Yeah, I would need to maybe see it again, or like because I think I saw part of it.
Did you
I'll link
publish
it
that
in the
one,
chat.
Alan?
I just swooped it and put it up today. I'll link it in the chat, dude. It's so good.
Nice.
Just absolutely obliterates the idea that a homogeneous medium lifts up images 1-to-1. The only example of that is them just assuming said medium, and when they go to do physical demonstrations, it's never analogous to what they say. Like it takes a drastic change in medium to create a boundary layer to basically capture an image for it to be presented in a different position for you in a way where it's not diffused and all fucked up.
Nice, yeah, dude.
Yeah.
He's laid out some things in here. I think as he's been coming with his ideas too that I've heard, and yeah, he's got some really good, like solid, like logical geometric components of it that, at least some of the times when he's brought it up in here, it's like there was really not able to be refuted in that way. There's no like direct refutation to it.
Yeah, he's crushing.
Kid's got a lot of heart. Is that what you say? Wasn't that like super eager and haven't been befoiled by the grossness of it all yet?
I remember when I was all young and Skipper, like, oh, here you are. And then and then people would say shit like, no, Einstein just says the speed of light can be anything. It's like, no, dude, I can't do this anymore.
then it's like, just years of that.
It's just whatever you want it to be. Yeah, but no, it's been a lot of fun, dude. But yeah, anyway, I'm heading off here. Peace, lads.
Cheers. Have a good night, Alan.
Bambi's awesome. Bambi would just come and ask questions like super genuinely, so everyone would just start whatever we stop what we would do and just answer them all the time.
Yeah, I just got here. Can someone give me the TLDR?
Well, it's whatever you want it to be now.
Welcome to Flat Earth.
Yeah, that's usually the sum of it. Nice, dude.
Welcome to Flat Sky.
More on point, right?
I missed.
Is it completely flat or is it slightly You think it's a flat sky layer within a larger domed hemisphere system, but the stars themselves are not hemisphere domed? I'm just asking. It's a question. I'm not really asserting. I'm just saying. Is that?
I have no idea. Who knows? How would we map it then, right? If we were to say like the whole thing about true position gets me crazy. I have no idea where a true position is for any of that. We've only ever seen apparent, which is already not where it is apparently.
I thought that was really cool. How Alan was saying that, dude, with like the ancients, because that would make sense. So that's how we actually live our lives. Like the sky is a mystery to a degree. We can measure to it. We can look at it. And we can measure just optically to it. So, but it would be a bit too like beyond your capabilities to consider that you would know exactly what it all is when you're on a huge, massive Earth. Essentially, you just from miles, and then you see this thing that you can't actually physically touch or access. We just see the sky. Like it would just like spiritually make sense of whatever it is on the grander scale has got to be just beyond what one person can see.
Yeah, they definitely got he said metaphysical with it, but it was more religious because they just were like, yeah, whatever's in the sky is not real. It's like angel. That's where heaven is. They have their conception of the cosmos, and I think we kind of vibe with that. We kind of think mostly as flat earthers. That's definitely where I'm at with it. Everything in the sky is kind of non-physical for sure. But the other thing about Alan's presentation is like there was this Chinese general who was sailing around the world doing stuff, making like history, and he was using this well-known method in shadow tables to do it. And they made a point to like obscure it from history, remove it from the books to make sure no one understood what he was doing. Deleted the treasure or whatever that he found, and just like deleted the whole thing. And in an obvious attempt to obfuscate the history that people knew how to celestially navigate before the whole John Harrison Ball thing.
Is there a recording to whatever happened in the last 2 hours?
Yeah, it'll be on Alan's channel, Space Audits, and then it'll be on the Earth Awakenings channels as well. I mean, the Earth Awakenings ones are going to be part of the larger stream, but if you go to Alan's, it'll be on Alan's channel, Space Audits, and then it'll be on the Earth Awakenings channels as well. I mean, the Earth Awakenings ones are going to be part of the larger stream, but if you go to Alan's, it'll be like right from the when the presentation started. The actual event itself, yeah.
Do you set space audits?
Space Audits, yeah. You can go on YouTube and all the other channels.
Thank you. Do you set space audits?
Space Audits, yeah. You can go on YouTube and all the other channels.
Thank you.
What's this presentation about?
Shane posted right there.
Our boy used the Theo method to use an eclipse to get a prediction for the height of the celestial objects above the Earth, and it turns out that the celestial theodolite shows the stars are in a flat plane above the level plane, but also the sun and the moon are also in a level plane above the level plane, as dictated by the predictive math using all the trig in the spreadsheets. So he used the celestial theodolite concept to show a new adaptation using the sun and the moon in eclipses. It was cool.
Wow.
So does that imply that the sun and the moon, maybe more, measurements in north and south would have to be made, but does that mean that the sun and the moon, from this perspective, or from that, what you just said, like would not be changing altitude ever? They're always at the same? Is that what this implies geometrically?
Sort of. It also implies that they're at the same distance, right? So the heliocentric explanation of a billion times away, but it just happens to be that much closer, and they happen to look at the same size. That goes out the window. They're treated ostensibly exactly the same because they have to intersect the path, right, to have that actual occlusion to use the prediction in the first place. But I think he did the whole celestial sphere. Like if you just put it at a spherical radius of 3959, which has to be linear, then the furthest geometric linear distance that would yield would be the 6210 across it. So I think he found the same thing.
Yeah.
The spreadsheets are cool. Someone was like, "That's probably AI," and it was like, "That's cool." But I mean, he did put all. I understand that he didn't add any formatting or do anything crazy, but a lot of people, when they just do a spreadsheet, they do zero formatting. That's cool. That's cool. It's all in the data. He produced graphs. He had 8 labeled tabs. I mean, everything's in there. Clearly, he put in work.
For sure. No, that's awesome, dude. Well, when you started playing it, I'm like, wow, what is this right here? It's like it was on point and just going through it all. And he's very clear spoken. And like I said, I'm probably gonna go back and watch that again because there's a lot of data in there as well. It also took me a minute, like the one like 6 million, like the meter one, like that's 39.59, and I actually like had to check that real quick just because I was like, wait, and to know that that's what's being discussed is essentially that 39.59. But in meters, I rarely think of that number in meters, like kilometers sometimes, but not necessarily meters. So that like threw me off a little. Not that it threw me off, but it just kind of I had to double take for a second to make sure I understood what he was saying there. And yeah, it makes sense of how they derive the radius from the sky, and then call it a globe and assume it's curved and say, well, even though it doesn't look curved or at curve, it's just refracting. And then, anyways, all the other stuff that they do, with this. But dude, the other thing I was gonna say is like, okay, it's kind of a separate topic, but like, how the angle of the moon phase like seems to sometimes be angled down and sometimes be angled up. One of the explanations has been said for that the sun and the moon are at different altitudes. Like during this whole cycle, the new moon to full moon, that they do actually change in relation to each other. But an eclipse is happening right at that moment, and if they're in the same, like, so. Do you think the sun and the moon are always at the same altitude, or do you think they only are during the eclipse? And do you think they change altitude at other times of the year? I guess that's kind of the question.
No, I think so. I know the sun changes altitude throughout the year, and then we know the moon does whatever the sun does in a month or whatever. So I'm assuming that the moon also changes altitude, but they would have to change altitude. And the thing that produces an eclipse isn't like isn't even the physical intersection of those 2 points. It's the optical intersection, as we were showing, right? Because that's what creates the shadow cone of visibility of the eclipse. It's only optically apparent to a certain portion of the people on the ground, because then you have to be at the right angle to have the sun obscure the moon at any certain point, and that the further you go, the less likely that is to continue because of the angular size of both of those objects, right? So I think that can happen when they're at different heights easily. It just happens to be that the visual path is intersected to your position on the Earth. That's what creates the shadow.
Yeah.
And I do think that the moon kind of fluctuates all the time.
Well, yeah, there is the 5 degree to the ecliptic difference, and how like the sun only goes to 23.4 degrees, whereas the moon goes to 28.4 degrees. It goes like 5 degrees more further, like when from the Tropic of Cancer and Capricorn, and then also just that like 5 degree tilt, which they call it a tilt. I'm not, but in the model, obviously, like the way the moon's offset, and then when you get the eclipses, it's the 2 points of the 2 kind of tilted orbits, if you want to call it that, or circuits. And those 2 points, like if you had 2 hula hoops, but you angled them differently, if you did that, you'd have only 2 points at where they intersect, which is the lunar nodes, which is what causes eclipses, or what is involved. You either have a full moon or a new moon that lines up with the lunar nodes, and the lunar nodes are like a 180-degree axis. There's a north one and a south one. They're always 180 degree. And then when you get a new moon or a full moon on those, you would get the eclipse, which is why kind of when they commandeer it, in my viewpoint, in the globe model and say that it's the tilt of a ball around, they're just relabeling what the ecliptic is and what that is. But like with all that in line, Shane, like, do you think that the sun and the moon are tilted 5 degrees from each other in the actual sky above us? Do you think that part is happening?
I think it very well could be, and that would explain exactly what we see. Like we know, like I'm pretty sure the sun tilt, like the whole ecliptic, the basis of that is the sun's change in height and altitude throughout the year. And to us, it appears to come and go. So you get the whole apparent altitude height. That's how you get the apparent motion of the sun over the year. I'm almost certain that that's because the sun is changing height.
Yeah, and then the moon having its like.
Yeah, I'm less certain about the moon because it's sporadic and it's like honestly, it does whatever it wants to do. It seems it does what the sun does over a smaller cycle for sure, but within that, it just has this like erraticness to it that's tough. Plus, you can't see it for a good portion of its cycle, so it's weird. If you do like the moon in a lemma, it's always missing like 3 points, but that 3 points like that. Those 3 points will sequentially like go throughout the entire analemma, so it cycles through itself. It's the weirdest looking thing.
Yeah, like when it's actually happening, where that shows up on the analemma. You're saying when the eclipses show up on the analemma, or when the new moon does?
There's a depiction of the solar analemma, and it looks pretty pretty coherent and you can see all the parts. But when you do the moon equivalent, the lunar one, like there's 3 points or there's a portion that you can never see because of the moon's face. So that portion rotates throughout the whole picture, and what you have is like this rotating 3-point gap that goes throughout its entire. It's weird when you're trying to say, oh, it does exactly like the sun, and you're like, well, kinda, but you'll never really know because of those 3 points. You'll never have all the data of where the moon is.
Yeah. Yeah, the whole like new moon cycle part of it all. Yeah, and the lunar lemma instead of the analemma, but yeah, if some people call it that, like the lunar either luna lemma or lunar lemma, but yeah, and it's like a little bit bigger than the sun's one as well.
I think I heard Alan say in the next episode he's gonna open it up more to the globers or whatever. I'm gonna bring up the southern hemisphere stars again. I didn't really want to go into it this episode, but next episode, I think I have some compelling info.
I mean, you can at any point just throw in one of the main talking points being southern stars, but that's really got nothing to do with if the celestial theodolite is physical occlusion times, in what way does southern stars change the physical occlusion time of a trigonometric prediction?
No, it's kind of a different topic, isn't it? Kind of more like how the stars move rather than like celestial theodolite timing.
Yeah.
But Shane, let me ask you let me ask you this. So in this image here, this is like the southern star rotation. Now, when they were at like 80 degrees south or whatever, like Union Glacier, or if they were at 53 degrees at Punta Arenas, that would be like, because that whole thing is 90 degrees. So obviously 53 or 80 along that. Like obviously 80 is pretty close to the center. So would you say they're at one spot above that one star trail? Or like the way it would be like if someone was 10 degrees from the North Pole and we look north, we would like on an AE type map, we would think, okay, yeah, they're right under that point. Was Witzit right under that star trail in one spot? And then if so, is there one South Pole? Or like kind of links in probably what Gatebreaker maybe was thinking about. But if we're going to talk about it a little bit, I just, that question came to my mind to ask you if you have any thoughts on it.
Yeah, I was trying to understand your example of putting the poles down, like for every GP of a star. I'm trying to understand the implications of that because I'm not sure I understand that because I think with the visuals I keep putting out, which is the globe model, right? It's the spherical latitude longitude grid of the celestial sphere of a right attention declination grid flattened out in the Gleason's projection and then spun around the Gleason's map. I think those are actual ground positions, like if you were to build the whole model out. But then we're talking about apparent, like, so if you're under the stars in your picture here, you have your apparent position. If you look like left and right, those stars would appear to rotate around you, sort of like in the model, like in the way that the model used to do it. Like, sure, the stars are above a flat plane, but you see them circling around you. But I think the only position that's really probably valid is the one right above you, because do all those have different south poles? No, I think that the south is like an optic convergence point. Yeah, something like that. So I think that the whole like understanding of ground positions versus apparent positions is still, I'm trying to work into that because I don't disagree with this globe model prediction of how just like the celestial sphere is splayed out. But that doesn't coincide at all with the apparent positions of southern circumpolar stars.
The idea is if you have a celestial sphere, okay, we have a celestial sphere, and then you splay it apart at the southern axis of the celestial sphere, the southern axis of rotation, the southern stars, that is splayed apart. And it being splayed apart, all those stars that are right next to each other are now on the edges of the post splaying apart. So this star plane or star circle plane or whatever it is, the stars at the outer edges, if we were to have a map with all the star names and we were to say, like, okay, on this corner of the plane we have this star, on this corner we have that star, on this corner we have that star, on this corner we have that star, those stars are actually, when observed in the sky, they're right next to each other, similar to Polaris and all the stars immediately around Polaris. That's kind of the idea.
Gonna need that in spreadsheet form.
that's southern circumpolar stars. I understand what you're getting at. But like, so this is the actual reported ground position of stars splayed out over the map. Here, I'll put the visual I just put in chat. That's what it is. Like that's what the model is when you complete the lower half of your observable hemisphere with spheroidal math, and you get the coordinate system representation of the celestial sphere, and then you splay it out across the world. Those are the known, reported, measured ground positions from a true almanac referenced at a certain epoch, spinning at 15 degrees per hour around the flat Earth. Like you'd get your specific latitude bands from these stars in those positions. What you're saying though, right, is valid. If on the outer edge, you wouldn't see them split out like this. You would see them as circumpolar in the south. You'd see them rotating around your optic convergence point, depending. Its declination will be dependent on how far south you go, right? Your latitude. Because as we pointed out with the celestial theodolite, we just found out, if you're in this observer-centric flat disk and you can't see forever, then as you progress either way, you'll only see the same hemisphere progress with you based on your latitude dependence. I think that's another important proof of that.
I hear you. I'm not going against you or saying you're wrong. I'm just saying, like, from my understanding, uh, is any way of mapping out the stars on a plane when they're sourced from the celestial sphere, when you have that celestial sphere and you split it apart, in this case it's from the southern axis, those stars that are actually right next to each other, not only on the celestial sphere, but observing it in real life, if we look at the southern axis of rotation and we were to say, okay, that star is that star is that star is that, when it's mapped on a plane, at least from all the ones that I've seen and even the ones I've made, those stars necessitatively are at the outer edges of this star plane. So if I were to put this star plane over the Gleason map and rotate that star plane, all those stars at the outer edges of the map, they're not actually there. In reality, as far as they're observed, the apparent, they're right next to each other. So the question becomes is, in what manner do they all of a sudden converge? I have like visuals this is very, very difficult to do with like words. I can't do it with words. When you guys speak and say these words, I have a tough time putting it in my mind, but I could see it visually. And just the idea is that any kind of like star plane with stars laid out with Polaris in the center, and then you go a little bit more down in latitude where you have the equator stars, and then you go more down south and you've got the eventual outer edges of these stars. These outer edges of those stars, they're not that far away from each other. Actually, this quite the opposite. They're right next to each other. So I don't like when I can't explain any more than that. But
Yeah. So can I jump? Yeah. No, I totally hear you.
Yes, please, thank you.
And I'm gonna play right into that because I'm gonna ask Shane. Like, so Shane, like, can you see? Are you looking in the chat? Are you still at your mic?
Yeah.
Well, what do you think of this first one? Because I drew this image. I'm gonna link it back to what Gatebreaker said. But this one, like, would you agree that like when they were at Union Glacier, they were like under the GP of some star in that zone? Do you think of it that way, or?
Yeah, sure. Because like the latitude dependency goes out as you go out, right? So yeah, that's the latitude band that they'd have to be under. They'd have to travel that far for that to be above them. Yeah, sure.
Okay, but like but if it was so is that in one location? Like the way the North Pole is in one location, do you think that is 10 degrees from that South Pole? Is that South Pole in one location? Or if you were to go out like on an AE type layout from any direction from the center, would you be going to 3 or 4 different spots if you're going to that center, or would you all end up in one spot the way you would? Because I like it with the Polaris, if everyone went towards Polaris, they would all show up at the same place. Would you say they would all show up at the same place with this, or is Union Glacier in one place? Like if everyone saw that and then started going towards that, would we all end up at Union Glacier, or would we end up in different parts?
Is there a GP under the South Pole? Is that what we're trying to figure out? Like,
pretty much. Is there? Yeah, like if there is one under Polaris, is there one GP under the South Pole? Yeah, that stays there. Yeah, that's ultimately what it kind of links to.
I don't think so. I think it reacts to the same as in the north. Like as you go north or south, it rises and sets. I think that relationship still holds. I just think it's an optical, counter convergence. I think the one in the north we can all physically go to underneath it, and I think that the one in the south would lead you just south. You go out towards the outer ring. I think that's just optics. So, which is why when you're trying so if you say to put a flag under every star that you see, you would get the globe, right? You would get this. Or you'd get
I would
this.
Well, like if you put a star coming out from Polaris or a flag under each star coming out from Polaris, I guess you'd end up with a huge, basically what a star trail looks like to us, but just of flags on the ground. But then that's the thing is is the one in the south actual or apparent? I guess that's really kind of the question. I'm just asking what you think. So like this image, I took a screenshot from yours, and then this is also what Gatebreaker I think was saying, is that all the stars on that outer green rim are all showing up as circles, almost like those darker circles I made. I just did it with paint with my mouse. Obviously, it's not so. And then I guess linking that in, if Union Glacier, it's they are there. Then on the outer edge of this rim, is Union Glacier in one spot, or you know what I'm saying? Because everyone can see that 10-degree point, over in South America, South Africa, or Australia, they would be seeing that rotation, and they could all point their fingers and say, that's Union Glacier, kind of like that first one I posted, with the arrow, that's Union Glacier. but then they'd be pointing to 3 different places and not one place. Whereas if everyone pointed to Polaris, we would all end up at the same place. So that's why I was asking, like in the south, do you think we all end up at the same place if we go towards the Sigma Octantis center of that rotation, or not? And then if so, like how could we decipher the differences of one or the other?
Well, yeah, no, because like south is always south. So so I think that when you're at that latitude where that green circle is that you drew, anyone on that, if you just go east or west continuously, then nothing in the sky will change. That will be at that latitude, at that elevation for any position on the plane all around the outer edge. I think that's what the stars look like. That's what the stars tell us. That elevation will never change. It'll look at the same latitude, which is where they get the globe from, because there would be a physical on the bottom of the globe would be the outer edge of these stars, which is where the projection comes from, right? The starting spherical coordinate system, that is the bottom half of the celestial coordinates projected out in a Gleason's projection, right, from the center. That is what it is. So to say that like the directions are obviously converging towards the bottom of the ball, because that's where the source comes from. But the differentiation we're trying to make is that's optics, right? We have a conceptual model based on a bottom that no one's ever seen. Everyone sees the first hemisphere. We're completing the bottom hemisphere with math. We're calling it the globe. We're doing calculations. We have a nadir opposite of the zenith. We're conceptually, mathematically representing the things that set in the distance. And we're saying they go beneath our feet. That's where we're representing them. And that's where this model comes from. That's where the star positions are mapped. Like we have mapped the southern stars that you never see. Like for every star you see, there's an antipode that's mapped conceptually with math that isn't actually beneath your feet. That is the model, and that's what we're seeing with the model, with the ground positions, and with this depiction. All the images that I show is that celestial sphere model projected outward. So I mean, I think what it's hard to represent, but I think that the difference comes between, is it an apparent ground position or is it like a real ground position? Because along the outer edge, it would look like the southern hemisphere is around the observer. But if you were to plot the ground position of those stars, you would think it'd be in a circle around the observer, as you drew in the lower left there with the concentric circles. You would think that's what it would look like. But then we're not actually plotting the stars we can't see anywhere. We're only mathematically representing them at the bottom of a sphere with a spherical coordinate system. And just because this representation splays out the bottom hemisphere to be represented this way, doesn't mean that that's not where the base is coming from. Because if you look up, right, you get the southern mirroring the north the further south you go. That's definitely what it is. And that's unfortunately what the model is based on. That's where they built it from.
Yeah, so you're saying the outer rotation is like a mirror that moves with you, kind of around the outside.
Yep.
Well, then let me ask this: like,
indistinguishable.
So let's say here's my movie plot. So you have a dude in Africa, and he's chilling every night. He sees the northern rotation, he sees the southern rotation, or some portion of each, because if he's near the equator or whatever, he sees half and half of each. And let's say one day he's like, dude, I'm going to run to this North Pole. Like, I don't care. Every night when I see the star, I'm going to realign my compass. And every day I'm going to hike and I'm going to go to the North Pole. He does that in Africa. Someone else does that in Canada. Someone else does that in Russia or whatever. They're all like, I'm going to this North Pole, And so you would, from what you're saying, like agree that they would all get to the same place. Like theoretically, like if they would get to the underneath Polaris basically, and they would meet there.
Physically, yeah, because they converge in the center and they'd all come across to meet.
So in the same scenario, but they're all going to say, forget it. I don't want to go north. I'm going south. Like I'm just getting to that South Pole. I'm getting in a boat. I'm going to walk. I'm going to hike. I don't care. I'm getting there, or whatever. If you want to bring in an airplane, make it easier for them. But let's say instead of the north, they're going to do the south one, and they're like, I'm going to the center of that rotation. Which like the pointer stars and the southern crux, like where they intersect there. Or Sigma Octantis, but maybe they wouldn't be able to see it. But either way, they could get to the center. So if every night they see it and then they redirect their compass, same thing, same guy, same thing, guy in South Africa, guy in South America, guy in Australia, whatever, and they all do that, you're saying they're not going to meet at the same place. They're going to meet at 3 different places on the outside of something like an AE or Gleason's type projection. They're going to all be at different, dramatically 1,000 miles apart.
Could be. Depends on the time, right? Because the south would be always towards the outer circle. I'd like to see that though. I'd be interested to see people if they actually converge at the South Pole.
Yeah, I mean, I've obviously never even been in Antarctica, so I don't have any like firsthand. But I mean, there is like ALE, which which the trip that Whitsitt and those guys took, which goes from South America, and then there is another shorter plane that claims to go from the Union Glacier to the last 10 degrees to the 90, and then I guess ALE claims they have a camp there. And then there's that company called White Desert from South Africa, and their trips are like more expensive. They're like $80,000. But those trips, they claim they go from South Africa to the camps on that part of Antarctica or whatever. And then they also claim that they have like a short little, you can pay extra money. Those camps are at like 71, 72 degrees, like in that area, but they're not near Union Glacier. They're on kind of the other area or whatever. But then they have like, if you pay extra money, you can get a flight to the South Pole, to the Edmondson Scott station, on that one. So that's, I mean, yeah, like, I mean, obviously I've never taken that trip. I don't even know if I've heard of anyone that I know who has taken it, but I know I've seen the website and all that. But those are more expensive trips. And then the McMurdo thing, people, military people claim they go from like New Zealand or Australia to McMurdo. And then allegedly there's also a short flight from McMurdo to the South Base Station. So, I mean, that's like as far as at least I generally know, like in terms of just some of the claim flights, that everyone would meet there. Like Whitsitt could have met there. If somebody else was on the White Desert side or whatever, they could have taken an hour flight, and everyone flies south. So that would be a way to actually verify. Like we could actually do it with South America and Africa now, just with the money to do it. Meaning, just if someone shell out, it'd be about 200,000 probably for that. So yeah, if we had 200 grand, we could actually just have two people go from at least those two. Maybe we wouldn't get the Australia side to see if they would meet, in the same place.
Yeah, I'm not even opposed to there being like a ground position for the South Pole. Those map projections that I play around with, like between azimutally equal area and azimutally equidistant, you can move like the southern pole projection. Like if you change your projection point from precisely in the North Pole on 190 to like 85, then the South Pole as a point, which was previously the complete outer circumference, becomes a point that's totally visible, and then Antarctica is no longer wrapped around the side, but it becomes a continent, and it becomes like what is the concave map, but it's just the same projection with a different focal point. So I'm not opposed to there being an actual like ground position beneath that optic convergence point. I just because I mean I don't think that the star map is the actual map of the ground. They merge them one for one. Like because every star has a ground position, because they can do that math, because of that relationship, they made longitude, latitude equal right ascension declination. They just decided based on the hour angle transformation or what time it is, 15 degrees per hour rotating above your head. They can tell, okay, they know exactly what time that star will be there based on that true reference point, and that's how they created the whole thing. I mean, I think that creating the ground from that and then projecting it to show us where it would be. I don't think that the South Pole is a problem. I would be interested to see if people who like leave in different directions converge at an actual physical point, if they follow the optic convergence in the sky though. I'd be super interested in that.
In Blender, I have the Gleason map as a base layer for the map. And then I have a literal celestial sphere of whatever size up ahead, and also the star, a plane with that celestial sphere splayed out. So Polaris is in the center, and the southern stars are at the outer edges. And I had multiple types of domes, large domes, a flat sheet, domes within domes. Like I tried every way I could to try to bend this light of the celestial sphere and the star plane to have it where an observer is looking south. They have either the outer edges of the star plane converge like how we see it in real life, which is all the outer edges together next to each other for one, and then the celestial sphere up above somewhere in the middle, small or big. Because the bottom of the celestial sphere would be the northern stars. So the celestial sphere is right over the Gleason map. So an observer in the North Pole is looking up at the celestial sphere, and they're seeing the bottom part of the celestial sphere. They're seeing the Polaris, which means the top part of the celestial sphere, the top hemisphere, is the southern stars. I couldn't figure out any way to get that top part of the ball to bend all the way around and have it hit the incident angle of the observer. Just hit the eye of the observer looking south. I couldn't do it, so I tried, but so that's just my findings, and I don't have anything like else I could do. So I just like share this info, and that's it.
Are you basically just saying I kind of tuned out a little bit, but I was listening, but I'm not just of you talking. I kind of was like doing something else for a second, but are you saying something like the red stars are all? There's that idea in a different wording, like that all those. I just had an image because I had my folder open. That all those
So, like,
reds are making like, a circular star trail in all those southern positions, and then back to like, if everyone, like in my analogy, that you got a dude in South Africa, a dude in South America. Like I said, every night they see that southern pole area, the southern center of stars, and they're like, I'm getting there. I'm building a boat. I'm going to hike. I'm going to take a jetpack, whatever it is, and they're going to go, And if so, like it just links into that idea as well, because you're saying not only how could they wrap around in that way, but then also if it moves with you, then if you travel towards it, you would be going to different locations.
Yeah, let me post this picture. I posted it.
I mean, that's all conceivably provable to an extent. Like with about $200,000, what then maybe the extra 20 grand for equipment. So that might cost like 220. So probably 220,000, and because both trips I think are like about 100 grand to do the whole like Union Glacier 90 South thing. And then to also go do a White Desert trip. Those are like the most expensive trips. The ones that those guys did were like 30,000, 35, but these are like 80, 90. So they're like 3 times as much each basically to do that, to test going from like South Africa and South America. I mean, even though like you could argue there's still things you can't confirm fully if you're just taking like a commercial flight. I mean, if you were to like chartered your own flight though, that would be a way that you could even verify more in terms of exactly what direction you're going and all that.
See that picture I posted? So I've got that stars mapped on that plane, which is off to the side. The middle of that is Polaris, and the outer edges of that are the southern star maps. Same thing as all the other ones we see posted, including the one you just posted. And then over there, I got the Gleason map in the center, and within that, it looks weird, but I have a literal celestial sphere, and I tried to incorporate. This is just some of the examples: domes, spheres, multiple spheres, like snowman, stacking them like snow. I tried to any way I could think of to what these glass spheres are doing is essentially bending light. And I tried to have the top, first of all, like I explained, I tried to have the top part of the celestial sphere, the top end of it is the southern stars. To have that bend down and around and hit the eye of the observer looking south on the Gleason map. And I couldn't do it. And so I took the celestial, first I did the star plane. So let's take out the celestial sphere, we put the star plane in there, and similarly try to have the outer edges of that star plane all converge to a single point, which is what we observe in reality, and have that hit the eye of any observer looking south. I couldn't do it. So that doesn't mean it can't be done. That doesn't mean I'm right. Everyone, that just means I couldn't do it. So that's kind of the idea.
Have you seen this animation? You probably have. It shows like a convex kind of lens, and it does cause those 2 rotations. This is pretty interesting for like certain ideas about it being a lensing effect.
Yeah. What I like the idea of this, but again, the idea with this is that black star plane that we're seeing, the whole outer edge of that star plane is the southern stars. So this glass dome being put on a small region will not suffice because it's not.
No, but what about this? Okay, so I'm gonna post a few images. This is actually Brian Leakey did this. It's the one. So this first one, he just took like a sheet of paper and he drew stars, parallel stars. And then this one, he put a dome. I think he said it was an upside down dome, if I remember correctly. So it might be upside down. We'd have to double check that. And it makes this effect. So I hear you on like the idea of stars going out concentrically. Whether this lensing effect could do that, because like the one animation thing I posted, it makes sense. It's kind of warping them around the outside, and potentially you could have some effect that would resemble that. It's conceivable, but I do hear you. It's only warping those stars in the one I posted 28 after on the one that's like animated. Those kind of stars in the south or the north, they are kind of warping, but it's only happening to those few stars on the outer rim. It's not happening to all of them around the outer rim. To go from like thousands of miles behind your head, around to in front of you, like tens of thousands of miles. So That, but it does kind of show the effect, but it just doesn't quite. I hear what you're saying, like incorporate how if they're all just only going out from the center. Now, if you have two things going out from two centers, that is getting into either the globe or a dual pole. You know, if you actually have two actual rotational points that have fixed positions on the ground.
Yep. So for me, the Gleason's just is out of the. Let's just the Gleason star layout is out of the equation just because I couldn't do it. That doesn't mean it can't be done. It's just I couldn't do it. Now for the dual pole, you theoretically could get the stars to project on a plane, but you'd have to, based kind of like that picture I just posted, the entire celestial sphere would be projected onto the whatever it is. It technically could be possible, theoretically possible. How I don't know, but there it is right there. So you could get all the stars of the celestial sphere projected over and like that, but not for the Gleason.
Yeah, like, and then this image I often post. I'll post it again because it's kind of linked to what you're posting. So like there's a sphere there in the middle, and then underneath the sphere you have the AE, or the azimuthal equidistant type of grid system, and that would be like of the southern hemisphere of that ball, because you could have one above it that would be for the northern hemisphere. So with a globe, you could take like the northern hemisphere and make an AE map, but then you stop it at the equator. You don't keep going. You don't expand it out beyond that, and then you have another one of the south AE map that goes to the equator and stops. So that's kind of how they describe the Earth as having the two hemispheres in their globe model. But I'm just saying you would have like two AE maps. But then if you go vertically on that vertical wall, those are the coordinates of a sphere projected stereographically. So you have the North Pole and the South Pole, with the equator being the straight line in the middle. So that's kind of what and that is kind of what is really what the sky looks like ultimately. It's like the two rotations, straight line at the equator, which is all easily observable for anyone on Earth to see either one of those. You know, you can do star trails with a GoPro or just with anything, you know, any day you want, of the north or the south, to see that there's these two huge rotations, and then how it goes straight at the center. So
I guess actually now looking at it, that shadow picture I posted, that might also work for the Gleason, because this shadow picture, you would have to basically have, that might work for the Gleason as well. But I mean, that's where I wanted to end it there. So.
Well, if you have a celestial sphere, like you know how those star charts, they have a northern hemisphere star chart and a southern hemisphere star chart, and they're like two AE maps in a way. And the way they describe that on the globe is they say, okay, you have the northern hemisphere of the ball and all the GPs and everything, and then if you flatten that out, you get one of them. And then if you take all the southern star GPs from the southern quote-unquote hemisphere of the globe, alleged globe, you would get all of those star trails and that star map, and then you could have two of them, you know, one on your right, one on your left, that would be, you know, two circular star charts, one of them of the northern stars, one of them the southern. Now, I understand how they claim that's happening on the globe in that way, but on a, you know, in terms of the way they kind of, in my viewpoint, commandeered that. But if you have like a two-pole planar Earth, then those would be the two poles, but they'd have to be on a plane, like you were saying. And there are other things that come in that would need to be figured out if that's the case. But I'm just saying geometrically, you'd have the two star charts. They would just be, well, you could literally do that. You can take the two star charts and you can put them on a table, and then there you have it. You have two circular star rotations on a plane, a flat table. Now, I'm not saying it's like a perfect one-to-one, but that gets into other, you know, how that's actually being viewed from the ground level. But I'm just saying you could have that. Whereas the Gleason's takes the one from the north and then expands it out and then kind of keeps going past the equator with, you know, arguably an assumption that it keeps going out like that, or if you know, folks have other evidences or whatever it is they claim that why, you know, or why that would be happening, that you'd have just the one in the north. But like you're saying, then you don't have another star chart that's a circle for the southern on the AE. You have kind of like a band around the outside, and then there would have to be some kind of other effect or something that would be happening, like some folks talk about like mirroring or something, you know, to, you know, have that happening potentially.